Alright guys, so this is day 3 here, and we were talking about the motherboard, the buses. A bus or bus is a communication system that transfers data between components inside a computer or between computers as well. Parallel, all data is being sent at the same pace and was faster in earlier computing. Serial, data is transferred in single file. So this is that's the structure, basic structure of buses. And so when I see you, I always see the clock. Okay, first you, clock, you. Okay, so okay, but yeah, it's not gonna work. I understand that. Yeah. Okay, so we were talking about bus there, and there's serial examples. For the serial examples are serial ATA or SATA, Universal Serial Bus, USB, IEEE 1394, Firewire. It used to be there. It's not more, not longer anymore. Peripherals. So normally SATA connection would be, if I when we see something we understand it better. So the type, this is first of all the connection that goes to the motherboard, and the other one goes to the hard disk. Hard disk is that device where you save permanently all the data, right? So that data is saved on a hard disk, and this type of cable that is connected is called SATA or SATA cable. There's an older type of cable here that is called IDE cable, and now again and again that topic is coming where we're talking about hard disk here. Now, if I just show you, this is how the hard disk looks like here. So this, um, this one, and here, this one, right? This hard disk, but I'm going to be taking out later, and then we're going to be exploring it from inside as well. That what is the hard disk? But hard disk here will be saving data permanently, and we're talking about just when the word comes SATA. Imagine this connection, this type of connection. Then the word will come IDE. Then I'll show you the other type of connection. Yes, ma'am.
I just want to see also.
Oh yeah, sure. And when I showed you on the motherboard, can you quickly also see where this connection connects? So, no. There you are. That took you like half a second. Perfect. We're here. Okay, two motherboards are connected. Wow. Because one side is connected to just one side is supposed to be connected to the hard disk, the other side is connected to the actual motherboard. So, oh yeah. Oh. Hey, the sound came in. There was a robotic sound that came. Oh, okay. Oh, it's not. Okay. I just wanted, I just have fun, blaming you or something. Oh, okay. So, okay, guys, we're saying that the SATA connection is there, and it looks like that. And where do you connect? That's also very important. But how much bandwidth? Okay, when I say the word bandwidth, ever heard of the word bandwidth? What does that mean in IT? Obviously. So it's the capacity of the cable to carry data, right? How much data can be carried. Suppose you are uploading 10 gigabyte of files and folders there, and the cable can carry, it's 1 Gbps, or 1 gigabits per second. It is showing, carrying there. It's just like if you have 2,000 cars and they're all going to one-way street there, right? So it will be the road capacity is not enough to handle that many cars, so they will slow down. So if you put a lot of data there on the cable and the bandwidth is small, so that's not going to also. So the bandwidth is according to the cable's manufacturer, how they create that. There is Mbps normally it is used in. So there's 400 Mbps, 500 Mbps, then it's gigabits per second. In 1 second, how many gigabits or gigabytes can be taken from that cable? So if you have per second, it takes like 1 gigabits, suppose, and you have 1 terabyte data there. So you can just imagine that 1,000 gigabytes, how would they travel where the bandwidth capacity is only for a cable 1 gigabits per second, right? So normally it will take then even weeks to upload. If it is 10 gigabits per second, so it's a capacity of cable that manufacturer normally
So here
carries.
the data means when you type in it automatically translates into zeros and ones.
Yes, exactly. That's the data. So, hey guys, we were talking about, but what overall are we talking about? That a bus in a motherboard would be carrying all the data to the different components, and then there are different types of cables there. There is SATA cable, which would transfer data from one hard disk to another, and I'll just dig down for the mouse here, so I could just create some diagrams, and I think it's kind of too much summerish weather here. Summer-ish. That's a new way to say. So I just hang on a second. Wow, I think it's messed up. After weekend, yeah. Okay, so we're talking about cables here. We're talking about motherboard components here. Then there is component interconnect express, which is PCIe. We talked about that before. Then there are many terminologies coming your way. We're gonna go and try to relate it to the hardware section where they are supposed to be connected. So PCIe and PCI Express we were talking about, and I asked you already. So it would be in the motherboard, those white slots there that are there, PCI slots and PCIe, and the cards that come here are these, which fix like this, right? There's this, the cut is there, but I cannot put it like that, so I can just go it this way, and the card fixes. This is the display card because it has a VGA cable here, right? So PCIe slots, VGA slots are where display adapters, sound adapters, and network adapters fit in, and these are the adapters. This is for display. If you're seeing a display, it's because thanks to this guy here, VGA, and there's a sound there, so sound chips will be there. But normally we put cards there if you want to put that display device with a lot of RAM, lot of sound capacity, sound chipsets are there, advanced features of sound are there, network cards especially you have to put there. Either they can be built into this like this, or you could put them as a card here in the full motherboard there. This is still kind of a review of what we were doing last week. So, but if you see the video, yeah. Mm-hmm.
Is it the component interconnect express?
Yes.
And the serial.
Exactly. So that would be going not as a parallel but as a serial, as a single file. Instead of 4 lines dividing the data, it will be a single line just taking the whole data from the display card to the motherboard to the other component, maybe hard disk. So parallel example would be include parallels SCSI, small computer systems interface. SCSI means small computer systems interface, SCSI, or parallel ATA or para. So when we talk about SCSI, we talk about synchronization or replication. There's a concept of data there that you want to update another component about the changes going on. So one component is making changes, the other component is updated regularly. Hey, I have a data here, so can you update yourself as well that hey, I have a data. So other component will say yes, now I have an exact copy of your data here. So that is called replication or updating each other. And there they talk about synchronous versus asynchronous. So synchronous just means that if one component is updating about its changes to the other component, there are 2 ways they can update each other: synchronous and asynchronous, right? We're just trying to understand some terminology. Normally this comes a long way with I teach a lot of other classes. That's where I create a lot of diagrams there, and a lot of other advanced applications as well. So if one component wants to update each other, there are 2 ways they update each other. One is synchronous way, one is asynchronous way. The only thing to understand here is that if it's a very very critical component that needs updating, So it will be synchronous if it is a delay. Yeah.
What do you mean by when you say updating each other?
So
Updating
a component may have some. So suppose there are two hard disks there. One hard disk has a lot of data there. That data has to be updated automatically to the other hard disk. Why would they want to have a copy of that data in the other hard disk? Can you tell me why a hard disk would want to have a copy of its in another hard disk?
as a
Backup. This hard disk goes down, the other one will have the backup of that, right? And the data will keep on being accessed from the other hard disk, right? So that is the concept of, if they want to update, we should know that either they are doing it synchronously or they are doing it asynchronously, right?
So
So
the update
mhm.
is only the copying the data, or is any other operations includes updates?
Update means copying of data. Exactly, that's it. It's a backup of data. It's a copying of data. So when it comes to synchronous and asynchronous, there really I had this. Okay. Oh, there it is. So you can see synchronous just means, I'm just gonna be quick about that. Very easy concept here, but we're gonna set it up or fix it or relate it to some of the hardware components here. Synchronous just means same time update. The update is going on here at the exact same time the update is going on here. This means that the replication has to be real fast. It will offer zero downtime. Whatever, have you ever heard of the word downtime before? What does that mean?
How fast it recovers from the failure?
Downtime is, downtime means not able to access anything or failure, but recover from failure, exactly. So after downtime has occurred, downtime means the thing is not accessible now, the data is not accessible. So downtime, 1 minute passed, okay, we are not accessing. 2 minutes passed, 10 minutes passed, we are not accessing, right? So how much is the downtime? So if it is zero downtime, the device may be lost, but still you have full access to that data because its exact copy is here as well. This results in zero downtime, which is the best thing that we can achieve when we have two hard disks and the data is updating to each other, right? So but the thing is that and with asynchronous, let's just it confirms all the data being changed here, confirms all data being changed in one device and then it copies that to the other device. So that is called asynchronous, the opposite of synchronous, right? So after it is confirmed here that the changes have been made, then the changes are made here as well. That is called asynchronous. Asynchronous is slower, and it has a downtime. It has a downtime, right? So when they are talking about synchronous and asynchronous, components need to update each other. Either if it's a critical component, they would go for synchronous update, which is I am being updated here and my other partner is being updated here at the same time, which means very fast update there and zero downtime. And asynchronous is for less critical updates there, where the component takes time to update itself or makes sure that I am updated first, the change was done successfully, and then it is sent on the other component. It may have a downtime if the device goes down because it takes time for the update to reach the other component. Now this concept we will be applying on many devices, and actually that goes to virtualization, to cloud, to all data centers. You will always keep on hearing synchronous and asynchronous updates, that applications update each other, servers update each other, clouds update each other, data on one cloud update the data on the other cloud. So everywhere this kind of synchronization going on. So wherever you see the concept, just try to understand first that synchronous means same time update, asynchronous means it takes time for the partner to get updated, right? So and this synchronous is there for data high, data and service high availability. Availability for data
Takes time means what it is doing.
service high availability. Yes, ma'am.
Asynchronous, it takes time means what when
So first it is confirming, acknowledging, just like if you have TCP, if you've heard about TCP, transmission control protocol in networks, that it wants three-way handshake. Hey, did the data send there? Did you receive the data? And the other one says, yes, I received the data. Here's an acknowledgement. So it takes, there's a communication going on. So here it first tries to make sure that the data is locally saved successfully. It takes time in that. Whenever it is confirmed, yes, the modification that I was making, suppose I opened a file, I made some changes and I saved it. Did you save it? Is it saved properly? Done. Okay, send the update now. Here, as the change is happening, the change is happening here as well. It's writing on two areas at the same time, which is right away you have a copy available. Yeah, in asynchronous it's not right away communication is there. So asynchronous, there's right away communication is there between the parties. So we just talked about this synchronous and asynchronous because components need to update each other through buses. We have this weird diagram where you have a heat sink showing here, and we talk about heat sink. So what is heat sink? Huh? Absorbs the heat coming from process, in this case processor, exactly. Do we see a heat sink here somewhere? We have a heat sink here. Heat sink does what? Wherever you see that silverish component here, it is heat sink, which means that the chipset below it is working so fast, so it's going to create some heat, and there is some device that's supposed to absorb that heat, so to keep the chipset cooler, right? So heat sink is used for that. So you will see the heat sink in many of the when type of processors here, and also on these chipsets, or on the motherboard, or on the display adapter as well, or any other adapter. So what we're trying to say here is that this is one big heat sink on top of a processor here, and there is another chipset here that has a very big heat sink here. This is kind of for a heavy duty motherboard where maybe the gamers use that, or a lot of where you have AutoCAD installed or Photoshop installed as big applications, and there's so much processing going on with big images that they really need the processor to be working fast, the RAM, the memory slots to be working a lot, and the VGA, the display adapter, PCIe or PCIe slots to be working fast if there's heavy application, right? So a chipset is a collection of chips, or and the chips could be French fries, or you could just go for the okay. So I like French fries. Okay, yeah. Mm.
What is component inter? What does it mean?
PCIe, right?
PCIe, but
SAS.
so what's the difference between the two?
So serial attached SCSI is the older cable that used to connect from a hard disk to the motherboard. And yes, there are so many hard disk related talk going on here, while the next slide is all about hard disks, right? So we're going to go in depth with that, what is SCSI. But right now, if you're asking about PCI, is for the display adapters there, right? And the SCSI is used for serial attached storage, would be for the hard disks. So display adapters and hard disks. Yeah, you were saying?
Okay, and what is parallel? What is the word
Yeah.
parallel used for?
So parallel examples include, now this was being talked about, that old way of sending the data from one device to another, and that was parallel cables. And that would be multiple lines. So if you have four lane road there, right, and that is or 5 lane road, so a lot of data used to go simultaneously. Okay, take this lane, take this lane, there's a huge data going on, and then now there's serial, so it's one fast road where you can just send the data right away. So that would be the parallel and serial in terms of what it is meaning there. So it used to be parallel, but it used to take a lot of, the motherboards were bigger than. Now serial way of sending data would be that small buses will be there.
This is serial cable, right?
This is also considered as serial cable, but they are talking about the way of sending data. The architecture of sending data is that it used to be bigger components, now it is turned down to smaller components with one line that is sending fast data, real fast data, because of the bandwidth. Before it would be bigger components components and so many lines through which the data would be traveling, right? So they're just talking about some of the components there, some of the way the data used to travel, and some of the way the data is traveling nowadays, and then how updates used to occur and is occurring. This is a current concept as well: synchronous versus asynchronous. Now, we have a chipset, and we talked about chipset last class as well. But here, when we say that what is chipset, so you should be able to just actually I can just show that quickly in the picture, and then we go ahead a bit faster. Now, some of us might. So first of all, I'm just gonna put a picture here, and you have a motherboard in main board or motherboard in front of you as well. So motherboard, computer. Yeah, early morning frog stuck in the throat. Grab it. Okay, so well, this is what you're seeing in front of you, right? So the motherboard here showing. Now chipsets would be this, a chipset doing some task. Normally you need to read in the manuals what task it is doing if you really want to go in depth. Otherwise, even in the manuals, they don't bother to give this kind of detail. You have to go onto the sites of the vendors and really request them, hey, what this particular chipset is doing. Well, what are chipsets? These are chipsets that are helping the main boss chipset or the processor to work and process all the requests of sound, network, and data transfer, RAM, whatever components are on these motherboard. The processor, the boss here, is regulating them and receiving the request from us, the users, and sending it to all the components. Hey, you got this order there. Okay, hey, sound card, turn on. There's a demand for that song that has been started there, right? Etc. etc. So the processor gets help from these chipsets, and in your motherboard, if you see, maybe you can locate some chipsets there. Normally, it's one or two chipsets that are showing there in the motherboards. But there are then, we were talking about, North Bridge and South Bridge, and what we need to know about that. North Bridge chipsets are for those chipsets that normally are near the processor. Now, suppose this is near the processor, and these very small chipsets are near the processor, very very small. This is very near to the processor, and these are, yeah, small. So whichever chipsets are near the processor, normally they are considered as North Bridge. So, but if you want to point out that, hey, which are exactly the North Bridge chipsets, and North Bridge, if I just go for the concept first, what is the chipsets are divided into North Bridge and South Bridge. North Bridge chipsets help processor do critical tasks, important tasks, if the applications, many applications are open, and then you're trying to close some of the applications, whatever is considered as critical in terms of the operations of the processor. So the chipsets near them are considered, those group of chipsets are considered as North Bridge. They will be possibly near the processor. They will help the processor do all the critical tasks. South Bridge chipsets, which are, again, if we go for the chipsets, they are a bit further from the processors there, and they're doing some less critical tasks there. So overall, this is the division between when you say North Bridge set of chipsets and South Bridge. So if I go back to that, front side bus FSB and backside bus, they also will go down to that, a set of signal pathways connecting the CPU and the North Bridge. So the signal pathways, the buses, and we already know what our bus is. I've just showed you that the very small line. Now this, if I could zoom it further, and if it has that kind of graphics capability, this picture may be a bit more in depth. So there's a line going here, there's a line going here, right? These lines, or if we go down to those architectural buses or lines that you can see on your motherboard already, right? So if they say that, what is FSB? FSB is set of those lines or buses that you can see on your motherboard right now. Yeah. So basically when I show lines, so you can just turn around the motherboard, and these are the lines that you will see, very very small lines, and they are in a very organized way. They are going from one place to another, and the lines can be seen clearly here, but you have to really look for it for very very small but organized way. The lines are going. Those are buses, right? And those buses are so if they are nearest to the processor, which is the boss, which is the biggest chipset, or the processor that is processing everything, so the nearest to them, if the processor is communicating with the nearest chipsets here, hey chipsets, help me do my task. So there are buses that are going from the processor, or lines that are going from the processor to those nearest chipsets. So those are called FSB, front side buses, because they are helping the processor do its tasks. Whatever double clicking we're doing, whatever powering on we're doing, and whatever's happening in the background, that all the requests are going to the processor. So processor is, you can say, regulating the whole thing, right?
So knob switches are responsible for critical tasks. So
Exactly.
critical
Critical tasks would be, yeah, critical tasks would be, suppose you're restarting a computer and the signals have to go, you're opening some application, you want to end task some applications because it's frozen now, so it has to be done now, right? And it can't wait. So if there are a huge set of applications already open, and then you're still opening some more, and it needs to check that now where do you open, where to get that memory to load this application now. So what some of the critical tasks are there that has to happen right now are there, but normally it's a very long list of tasks that they consider as critical, and the less critical are in the background applications, background processes. Some application you never used, so calculator, suppose you never used for last, or some game, card game there inside every Windows operating system. It's just there, its service is loaded in the background, that's it. It's not doing anything. So but it has to be loaded once at least, so that's a non-critical task. Okay, load it and that's it, right? That's just one example. There are long list of examples where services are running in the background, they're just running, and very few commands come from there, very few requests come from there to the processor to do anything, right? So now the communication between the processor and the nearest chipset is done by these buses, front side bus, and communication between the processor, if present, backside bus, if present, is a set of signal pathways that connects the CPU and L2 or L3 cache. Again, quiz question for last week students. So there are this week students and there are last week students. So this week's, well, we are all students, I'm just kidding. So here, L2 cache, L3 cache has a purpose. You got an assignment, and that's very good. You guys sent the assignment. Like one guy did not. I'm not looking at you right now, Avas. Just kidding. I am. So but others have sent the assignment. So today Avas will be sending the assignment as well. Previous assignments, right? When you're smiling, this means no way of teach. Don't expect from me, right? Or is it like, yes, I'm determined to send you the assignment, teach? Is this smile meaning that? Oh, okay, so but it's your benefit if you do that.
I forgot to take a picture.
Hmm?
I did it in my house. I forgot to take a picture.
You should take it with a selfie, right?
And I was inside and I was like,
Good.
but I forgot to.
Yeah, you can just show me even now, or you can just email me that picture, right?
Yeah,
Cool. So you did it, right? That's
Yeah.
good. So L2, L3 cache. What is cache? Quick one. What is cache? What does it do?
Data got stored in the hard disk in
Low.
order to help the. Sorry.
No, I was just doing this.
In order to help processor load tasks.
I think that was page file. Page file is a file or area on the disk that is used as RAM when you run out of memory or RAM. When you're loading applications on top of RAM, and so much applications have been loaded on the RAM that RAM says, whoa, okay, there's no more RAM, and you're still double clicking that MS Word file there. So that MS Word file that you've opened now, and there's no place on RAM, some portion of the disk is used as a RAM or a memory, right? So to load the application, RAM loads applications and runs them. And hard disk saves them permanently for long-term archive, right? So page file, you're talking about page file. So that is page file. You can just update your notes, right? But what is cache? Temporary. You're saving some data locally, so it could be accessible really fast. Cache is locally saved data that could be accessed real fast, right? So that is cache, and it will be used in all applications. It's used in so, but L2, L3 cache for processor. Now processor, if I just go back to the diagram here, and there was a diagram here, and it's not there. Okay. Oh, it was, sorry. Third one, right? Oh, this one. Ah, okay. So here, when we talk about that motherboard, so we are talking about
Sorry, what
this
was the
L2 cache, huh?
what was the technical
Page
definition
file.
for, what
The
was the technical definition for cache?
Yeah, cache is locally saved data for future fast use. Let me just write that. Locally saved. So cache, it's in the slide, and you'll be I'll be showing you slides as well. Cache, or some people call it cache as well. It doesn't matter how you call it, refer to it. This is locally saved data for future fast access. Future fast access. So it is. There is. This room is warm, right? It's not just me. I'm perspiring right now. I don't know why. Should not purchase shirts in winter, right? Okay. So anyway, so locally saved data. So this is going to this should be clear to you that if you say, oh, where's the cache data? Is the data being cached right now? So this means for future fast access, is the data locally being saved there? And yes, that is temporary always, right? So because then that data has to be replaced by other data that can be accessed. So it's kind of queuing as well. You put the data there, and the processor will access it from here instead of from any point that is further away. So here L2, L3 cache is just those chipsets from where the processor reaches for the data that it needs to process. So if we go for our diagram here, and if I just can make some more pictures out of that diagram, so I'm just gonna grab this diagram here and put it on MS Paint. That's the latest. Okay, that's not latest, obviously. So this is the motherboard here, and what we're talking about, if I could just make it much bigger. No, it's not showing the L2 L3 cache. So I showed you last time L2 L3 cache. If I can take out that processor, so processor, last time we took out that processor as well, and that is, see this, I'm doing this, yeah, like this, right, or back and this, right, and then take it out, right. So seriously, it's not showing here, but okay, it's very small in every motherboard. It's very small. Oh, it's showing there in the middle of the processor socket. Thank you, ma'am. See this? In the middle of the processor socket, there are very tiny chipsets. But okay, this is where you can locate it easily. Can you locate it on this motherboard? Where's the cache? So within this tiny socket, you see small chipsets, right? These chipsets are cache. Now the processor receives a lot of commands. You're opening MS Word, you're opening PowerPoint, you're opening sound, you're opening YouTube. All these commands the processor has to process, right? So they are, for a very small time, they are cached or locally saved in those chipsets, and at once they are queued, and the processor is just processing them or executing them right away. There's a sound card, there's a display card, there's a YouTube, there's a any application loading. All those commands are going there to the L2 L3 cache. They are stored there, and where's the cache on every other motherboard? This is the easiest one that I showed you. It's in the middle of the socket. Exactly, please locate this on your other motherboards. This very small silverish chipset. This is not like other black chipsets there. This is a chipset, right? That's the example. We're not looking for that. We're looking for this, the silver cache. Silver. Where? Yeah. So it's there. It has to be always there. It's just that it's not in the middle of the socket. Yes, sir? You were saying?
So where would it be?
Right, very nearest to the processor. Locate that nearest to the processor.
Is this right?
Yeah. The silverish chipsets are all caches. L2, L1, L2, L3 cache. Right?
What is the difference between L2 and L3?
Yes. L1, L2, L3 caches have their own different purposes. So, did I took it out from this one? Oh, this one. So yeah, you can just put it. It's like it's a good exercise to put it back as well, and try to put it back in a way that we took it out, and that's a very good practice. So ma'am, you, because these have all done that last week, you have to put the processor back, and you can see there are pins, right? We cannot bend the pins, although this is okay. This is not a real one. This is not gonna work anymore. So try to put it in a shape, in that shape. It's gonna go only one way there. Like there is no other. If it fits naturally in, this is the correct way. If it doesn't naturally fits in, we don't have to put. And then keep the changing sides. Normally there's a arrow there that has to match with an arrow somewhere on the socket, on certain side of the socket. Yeah, you can just keep changing the side. That is also one way to figure out. No. Change again. Yeah. So keep changing the side until one day, you know, no. So I have to. If it fits here, not fitting. Oh yeah, we have this. You know, this is the arrow here. This is the arrow, and see this, the arrow here. It has to fit on any one corner, right? So and try to make sure that this is back. This is like. Oh, I don't fit, but there, it is bent. That's it. Okay, yeah. The pins, some of the pins are bent because somebody in the previous courses actually gave a force when it was not fitting, so the pins are bent now. So that's why it's not. It's still moving. Otherwise, if it moves, it's gone already. Right, guys. So what we're talking about is that the chipsets, the north bridge, the south bridge, the L1, L2, L3 cache, but we need to check out what are those and what is the functionality, overall functionality. If we the question is actually why L1, L2, L3, why not just one cache, just L1 or just L3? So if they are different, there has to be a purpose for that, definitely. So let's go for that as well. Actually, it's coming in the slide that what is the purpose of that. So I'm just gonna go to the slide here. And if we go, well, for the north bridge, we talked about that subset of a motherboard chipset is the set of circuitry or chips that performs one very important function, management of high-speed peripheral communications. And then south bridge is the south bridge subset of the chipset is responsible for providing support to the slower onboard peripherals, and it's all that work that is not critical, and that is not very so it's slower work, and that is high speed. When it comes to north bridge, it is high speed. When it comes to south bridge, it is slow speed. It manages any component other than CPU, memory, and cache, and PCIe slots, right? So whatever is fast is handled by north bridge, and later you will see that all the critical tasks as well is performed by that. So guys, all the faster components are done by north bridge, and all the slower components are handled by south bridge set of chipsets. But we were talking about caches as well. I'm going to be coming to that. In fact, let me just grab that because we asked about that. Now, maybe for some, it would the task would be this would be a bit more familiar. If have you ever seen this screen somewhere else? No. This means that I have worked on Photoshop and really worked hard for that. No, I just, somebody's hard work. I did say thanks to that guy. Yeah. I just had to make slides way back, so I said, Hey, somebody already did that, because I don't have to, reinvent the wheel again. Seriously. So, but the main thing is that how do we really talk about it? What do we exactly talk about it? So, L1, L2, L3 cache is the question. There are other topics actually coming our way, but let me just get that because I'm sure I saved it here. Um, hmm, hmm I just wanted to give the proper definition for that. Otherwise, the main purpose overall is that it's going to simply save the data in L3 cache first, and then it will save the data in L2 cache. It's like queuing, and then it will save the data on L1. So when there are huge amount of tasks coming from the components as well as the operating system as well as the applications. So components, what are components? Sound card, network card, display card, right? And they are being used by applications. So you open YouTube and there's a sound coming, it has to go to the sound card. You open YouTube movie, it has to be shown through display card. You are accessing sound and display on YouTube with the help of network card. How? Obviously from internet you're getting all that. So sound, display, network card are always being used. Why? Because you're double clicking on YouTube. So all that requests are going to first L3. They're staying there because there are already requests in L2. They're staying there because there are already requests in L1. L1 are the requests that processor processes. When they are done, L1 says, hey, my tasks are done. Okay, L2, bring more tasks there. And the L2 tasks are moved to L1 and then they are performed. And then L3 moves their task to L2. So this is like you're queuing up the task and processor is executing. Okay, turn on that sound is there. Hey, sound card, you got it. So I'm sending that request to you. Create that sound in the speakers, right? So all processor is processing all those requests with the help of L3, L2, L1 cache. So more queuing up is there, the better organized way. You won't see an error when you see, oh, I can't hear a sound because the processor was too busy doing something else. Either processor was slow, maybe it was not 1.7 gigahertz, maybe it was 1.2 gigahertz, maybe it was megahertz. I don't think anyone has megahertz anymore, but gigahertz processors are there. If you have 3.2 gigahertz processor, that's a wow. So your task of multiple application opening, so much going on the one computer, and there's a game also there somewhere paused in the background. So every task will be performed really fast because of the processor being fast, and then it's being organized with the help of L3, L2, L1 cache to queue up all the tasks and execute them in an organized way, right? So those cache will be used for organization, but there are more slides coming which will be telling you that. But what we need to understand from the processor architecture here is that it's a socket that is, it can be dual socket, it can be three sockets. I'm showing you just this motherboard. Otherwise, this same type of socket is, you can have two, you can have three, you can have four sockets here. So the motherboard will be much bigger there. And you can this is normally used in big data centers for banks, for insurance companies, for hospitals, where there are very heavy applications are working right now, right?
What do you mean by socket?
Oh yeah, so socket is the terminology used for the processor. This is a socket. This is a PCIe slot for display adapters like display card, network card. This is the RAM slot. You put the RAM there. RAM is used to load all the applications on them, right? If you shut down the computer, applications will be shut down as well. So RAM, on the RAM, applications are loaded, and then they when you power off the machine, they are unloaded from there, and so they work on RAM. What? Data and applications work on RAM. They live on hard disk. They always live and sleep in hard disk. When you power on the computer, they start loading on the RAM. The more RAM you have, the better performance is there. The less RAM you have, they will start slow. They will load applications. This is a RAM slot. This is the PCI slot, and this is the socket for processor. The naming is different. These are called slots. They're memory banks also. This is called slot, PCI slot for display adapter, sound adapter, network adapter. This is the boss here, the processor that is processing all the information. But we have gone in detail in previous classes as well. That's why I'm just trying to repeat that for you guys. Otherwise, there are more future topics. Yes.
If you have a faster frames per second display, does that mean that if you were to have more RAM, your display would be more fluid?
It will be more towards display adapter and its RAM, display adapter and CPU also. There is also called a GPU. If you've heard of that, graphics processing unit, that is the main. So the processor here has the capability to help the display adapter as well. So it will have GPU capability as well, graphics
that
processing,
wouldn't have
plus the display adapter.
that wouldn't have anything to do with the actual RAM
No.
itself.
The RAM would load all that heavy application on it, but how to move the frames per second,
Yeah.
that will be done by GPU, graphics processing unit, and the display adapter, the gaming display card. One card is adapted $600, $500, because of what it's doing. Loading frames per second are amazing speed. So you see very deep graphics, for the games, and all the details are there for the games, right? You're a gamer, right? Basketball gamer? Gamer mean outside basketball. There are also games, right?
Yeah.
Gamers? No. Okay. So, okay. No. So here, when we're talking about motherboards, so the major components should be in mind, and then we talked about a Northbridge set of chipsets and Southbridge set of chipsets, and then there are these PCI expansion slots that we talked about. But what are the bandwidths of those? Peripheral component interconnect, or PCI. Normally in interview, abbreviation they may or may not be interested in, but what do? They would be very interested in interviews for that, right? So PCI and PCIe, the difference. They would want to ask the difference. So you can say peripheral component, right? Okay, good, but what do they do? So that's where the question starts, actually. So the more you can just say right away, the better. So PCI we have shown already here. So which ones in color are PCI slots? Give me the color. White? White, exactly. Are PCIe slots. So PCIe, smaller white. So PCI slot, anyone knows the bits? Now we did talk about, okay, what are the bits? Okay.
Is it PCI 16 and then 32 and then PCI X is 64?
PCI X. Okay. Because that is upcoming in the slide now.
PCIe is 64.
So we had a very old motherboard here as well. I guess the slot that is even longer than this. Do you have in front of you that motherboard? No, these are a bit more newer. That was old. So there was a much longer PCI slot where it was 16-bit. 16-bit would be much slower, and then 32-bit is this, and this is 64-bit. So the rate of transfer of data is much faster here with PCIe, and with PCI only slot, it would be 32-bit network cards or display card, or sound card would be there, but they would be slower. This would be faster here. Anyone knows the purpose of this battery here? Yes. What's the purpose of this battery?
That's to have the BIOS setup on it. Is that all the information for the BIOS setup? All the data?
Is saved here, exactly. BIOS. You talked about BIOS. What is BIOS? Ever heard of that? Basic input output system, not per second. Yeah, but what is BIOS? It does something. Okay, so brain of the computer, one thing, but if the interviewer says, what does that mean? Or anyone says, what does that mean? Brain of the computer means what? CPU is the processing unit, central processing unit, right? So, and that would be CPU. But BIOS is where you can configure the hardware and components of that. Suppose you say that I don't want to just use this slot here, a PCI slot here, right? I'm gonna disable this. Now you disabled it in the BIOS, and somebody comes here and tries to put the display card and network card here, not knowing that in the BIOS you actually disabled this component. So somebody's trying to check that, and hours after hours it's not working, and then you said that, oh, I disabled in the BIOS, so that's why it's not working. And it's really, why don't you tell me? So the thing is, within the BIOS you can handle the security of the hardware. Within the BIOS you can handle which component should work, which should not work, that which hard disks should be working, which hard disk should not be working. So whichever component you want to disable, you can do that. You can change the time there, you can change the security there. And ever heard of boot sequence before? Boot sequence of a computer. Boot means what again? Boot means start. Hey, boot the computer or reboot the computer. What is reboot? Restart. So boot sequence would be then what? Sequence of booting, sequence of starting. So it would be, do you want to start with network adapter? Suppose if there was a network card here, or you want to start with a hard disk. If you wherever you have an operating system files, it will start from there. So when you power on the computer, it is called booting the computer. When you restarting the computer, it's reboot. And boot sequence just means that you have should the computer start from a network card, should the computer start from a hard disk, wherever it finds the operating system files, it will start from there, right? So we're using those terminologies because we're going to reuse them in future discussions. Speed 64. And yes, so if you have 64-bit speed there for the display adapter, your bigger graphics will be in much deeper detail, much clear landscape is showing, and it's amazing, right? So because of the speed of showing transfer of data there, it's showing those. So if we go for that, PCIe slots here, 32 bits wide, running at 32 megahertz, and 66 or 66 megahertz. So if I just put that slide up, and am I recording that? Yeah. Okay, so here you would see these PCIe slots, and they are 32 bits. So you know the difference between those slots, you always go for the cut here. Where is this located? So any card, any display adapter that can fit here will never fit here. You know why? Why? I just said that. Because the cuts here is there, so the card that fits here can never fit here because the cut is here. It won't fix here, right? So always go for, and that's the beauty of the computer, that it will only fix one way. There is no other way that, oh, you put it the other side and it connected, and now it's not even working, right? It's gone. So it will only fit one way. That's the best thing about the display, about the motherboard and the desktop and the laptop connections there and the ports. So we understand that the PCIe slot is 32 bits, and PCI they're 3-inch long and logically wide, typically 32-bit or 4-byte with speeds 33 megahertz or 66 megahertz. Not a lot of speeds nowadays with 133 Mbps. What is that? Ever heard of that? Yeah. Megabytes per second. That's the transfer of data speed. And 266 Mbps. Actually, megabits per second, respectively. 64-bit PCIe slots exist for older servers. They double the above speed. Seriously, for older servers? Are you kidding? So, but the thing is that 64-bit PCI, they're saying that there is a version of PCI which is 64-bit, which used to be, and they were on older servers, right? So, but now it's PCIe. The cut is different. The shape is smaller. The shape is different, right? So 32-bit cards can be installed on 64-bit slots, but not the reverse. What does that mean?
Because the 34.
Mm-hmm. Yeah, you were right. Whatever you said. Yeah, just kidding. So yeah, you were saying
64 bit slot cannot fit
32-bit cards can be installed on 64-bit slots.
Yeah, the 64 bit size cannot be
In a So reverse is not possible. So older can be on the newer slot. Older card can be on a newer slot, but newer card cannot be on an older slot, right? PCI slot because of the shape also. PCIe, so that is also, oh sorry, PCI X, visually indistinguishable from 64-bit. You see it, you will know it right away. It's PCI X, right? Because it uses the same slots. PCI extended PCI X takes the 66 megahertz maximum frequency of PCI to new heights. Targeted at server platforms. When you say server platforms, so do we mean this guy here? Server. When we talk about server, there's this desktop here, there's this desktop here. Are these called servers? What are called servers in IT?
Oh, server.
Offering the services. So servers and desktops, what's the difference? Anyone knows? So they're gonna mention that a lot. So suppose it's HP company, Hewlett Packard, and they have HP server there. And if I just go to images here, so these are big machines. And why are they big machines? Because thousands of users are connecting to them. Servers are big machines. So banking applications, any other government applications, and insurance company, hospital, big applications where thousands of users are connecting, those enterprise grade applications are always installed on servers here. These servers could be 2,000, 3,000, 4,000, up to 10,000, $20,000 in price because of the components on this level. When one machine is expected to receive thousands of connection from 9 to 5, and it's 24/7 365, 9 to 5 every day, and 24/7 365 the whole year, round the clock. They don't shut down, they just keep on running, right? So that's why you have an application on two servers, one active, one copy, right? One active, one copy. So these are servers. So if thousands of users connected to that, and desktop would be desktop. Obviously thousands of users will not be connecting to that. So thousands of users will have their, each one will have one desktop. So from those thousands of desktops, people will be connecting to the application that is installed on a server. So it's a heavy machine, it's a big machine. Rack servers, there are tower servers, and there are other types of servers that do the equally critical work, but they are called blades. Ever heard of blades before in IT? So blades are, or HP blades, blade servers. So this is also hardware, but blades are created for space problems. So if we go down here and if we try to check that, so these look like very small discs there. In fact, if it is retrieved from somewhere, so you could see the size there. Blades are okay. Oh yeah. So oh yeah, this is a blade. Now are you able to see that? So if I just make it bigger, so you see very small, this could be a bit longer in length, but you can see the width and height. So this is exactly going to perform like this server, rack server. Why? Because it has all the RAM, processor exactly the same, it's just size is smaller, that's all. So that's why it's double expensive, because it saves a lot of your data center space. Remember that blade servers exactly perform like any rack server. These are called rack servers, and thousands of users will connect to the rack server. Thousands of users can connect to the same blade server as well. But the main thing is the rack server will take a lot of space, and you can have fewer rack servers in, suppose, this room, and you can have a lot of blade servers in this room as well, right? So rack servers will be fewer, blade servers will, obviously, they're just taking that much space. Why not having that? So, but the companies who can afford that, banks, they always have then blade servers. Now you can see the combination. Below is rack server, above is blade server. Yeah. Very big cost difference. Blade servers are much, say, they do the same task, but they cover a very less area. So it's more than double the price of a rack server. They're expensive. Oh yes, exactly. So in the blade server, you will install an operating system, Windows operating system, You will install on top of that a banking application. Suppose it's a bank. The same thing you will do it on the rack server. In fact, this below one is a rack server, and above one is a blade server, right? So this is till here just one server, and this is just here the same thing, but in this size, right? So that's really amazing, and oh yeah, and that's how it just looks like when it is outside. So we see that there are server types there, and so the server grade RAM will be more expensive. That RAM is made for it. You know that the server will have thousands of connections, thousands of people connecting remotely. So the RAM is of a server is much faster than the RAM. So 32 GB RAM of a server and 32 GB RAM of this desktop would have different speeds. That is a server grade RAM. Still 32, 64 GB of a server would be much faster, and you can fit it only on the server, obviously, not on desktop, right? So you would know that there are two major categories of machines there. One is desktop, and that is for one user. One is a server, that is for thousands of users to connect remotely on. And the servers have type. There are tower servers. Well, tower servers are standing one. Rack servers are laying one, and the blade servers are actually just very small size. They all do the same thing, right? So we understand that. Let's go ahead, and when they again mention here in the hardware that this is for servers, you should have a picture of rack server, blade server, tower server. Tower is the same server standing, and the same server lying down is rack server, right? So have a picture in the mind always when you are trying to go ahead and understand everything, right? So now we understand targeted at server platforms. So obviously PCIe X, better performing card, and huge data, huge display data. Suppose there's a big game there, big actually video there for a product for a company, and that video there are some shapes of the products there that are created in Photoshop, and some of the images, just one picture, some of the pictures take like few hours to be converted into a picture that is showing something in deep details, right? So sometimes it takes hour to render. That is called rendering process. Render the picture, right? So what we're saying here is 64-bit. So it is for PCIe X is for server platforms, and parallel interface that is backward compatible with 32-bit as well. So backward compatible just means that if the server had the slots for 32-bit, so 64-bit would it can be placed there as well. It will not then perform on 64-bit level if it is placed on a 32-bit slot, which is the white ones here on the motherboard, right? And the card that I showed you already, we're talking about that. So, but these are just the technical details there. 66 megahertz or 533 Mbps, 533 megabits per second of data can be passed. This is a 64-bit slot. 64 times 8 equals and then equals 8. So 8 times 8 is 64, right? So therefore 66 times 8, 533 megabits per second. Now they're converting the megahertz into the data, actually the way it is trying to be sent. So these are some of the details that you can see later as well. Well, okay. But the thing is that you should understand in hardware that it goes down to 64-bit, and normally you would have now that in some laptops as well, especially those gamer laptops. One company, maybe some of you have gamer laptops already, or though someone who have gamer laptops. So there's one category called, or one company called Alienware. So that has pretty much server grade kind of hardware. It is one laptop is $6,000. The gamers go to that level, right? So, hey, Dad, give me that $6,000. Okay, no, okay.
Is there a software called Alienware?
So it's a hardware. Alienware is a laptop that is heavy duty, that has the best display card, the best RAM. It goes up to 64 GB support. Now these these desktops might go up to 32 GB only maximum RAM. They go for a lot more configuration. So we're talking about then PCIe X, that is 64 bits wide, 133 megahertz, and this is how if you see that it would look like this. It would have different types of cuts there as well, that you could just notice from there and understand. Now this, I was saying 64-bit PCIe, and that is this small one, PCIe, right? Otherwise, the other ones will be. So we're talking about the speeds here. That's what we need to understand. And if we go down to then mini PCI 32-bit slot. So this is mini PCI. This is the same thing we're seeing here in this picture. So what is this picture? What is the device in which we are installing this? This is the same PCI. So you're saying laptop. Do you agree to that or do you disagree to that? So this is the motherboard showing, and you can imagine the display card that I connected there could be on this slide. So this is the mini PCI. It has to be a smaller device. So yes, it is a laptop. So in a desktop it would look like this, the white ones here. In a laptop it would look like this, the same thing. You're attaching a card there, an adapter there, and that adapter could give you, maybe it has 64 GB RAM, 32 GB RAM for the display, for the gaming, for Photoshop, for AutoCAD. But in laptop it looks like this. That's what we need to see and know there, right? So when we say adapter, we keep on saying adapter. Have that picture in mind, that the adapter fixes. In fact, you can fix it, then you can take it out, then you can fix it and take it out, because we all did that already. And give it a after that, give it a good push on once you, yeah, it's just more push there. And just taking out, there's a lock there at the end. You have to move that white cable. Yes, move forward or backward, and no, move the cable plus pull the card. Move that, not cable. Yeah, that. Okay, you got it. Otherwise, see this? Yeah, see this? There's a lock here. You can just pull it like this. Pull and then pull the card, and it will be out. Right? So you can use. Yeah, sure. If that VGA slot is there, yes, because it will fit in any one type of only slot. Anyone? Yeah, try. Did I say? I just said good, and I wanted you to discover that. Give it a push now. Like, is it fixed? So if you pull it now, yeah. Now, okay, now remove it from there. Okay. So, yeah, we all did that last class. But if you want to do that, yeah. So here, then there is XO. Okay. Thank you, ma'am. And yeah, so display adapter. Whenever you talk about adapter, just have this picture in mind. This is a display adapter, but normally it's now built in more coming here. Then, and things are going smaller and smaller. Although desktops are still really popular, but it's going towards laptops and tablets. Okay, so we also have this category called PCIe slot. So single lane and multiple lane. Now, many motherboards you might not see this architecture, or you might see this architecture, right? Depends on, suppose you're a programmer, you're a developer, you're creating applications for hospitals or banks or for government. So you would go for certain type of desktops that does certain type of tasks that are related to your profession. So doctors would go for, or AutoCAD engineers would go for some AutoCAD related applications. So depends on what kind of work you have. Suppose you're a designer, you will be opening Photoshop, and that's a lot of photoshopping and rendering you need to do. You need a lot of memory, a lot of display power. Suppose you're a developer, developers create programs, they don't need display power, they don't need display cards like these, or $600 just display cards just to view a very big picture or a lot of streaming video there. So you would go for that kind of motherboard where you know, if you need a display adapter or you don't need a display adapter, you just need speed of the you know, network card, speed of that motherboard, but not exactly the display. So what PCIe we're talking about here, and this is shown in the motherboard, right? But it's not in every motherboard. So do you see a very small E in the motherboard in front of you? I don't see it here, right? So this means some older motherboards are there. This means newer, but the PCIe would not be in this chip. Oh well, I actually, it is there. So this one, small one, right? But it's not in every motherboard, right? It's not in every. It's not in there. Yeah. So some motherboards will have it, but not all motherboards will have it, right? So depends on when did you buy it, and then you know, how, what was the purpose of buying it. You really want speed there. So PCIe lanes, there are 2 gigabits per second or 4 gigabits per second lanes. That translates to like, this is the data that they can transfer, which is not megabits anymore, it's gigabits now, right? So PCIe slots, we were talking about megabits, which is slow. Now it's gigabits, and it can go up to 20 gigabits, 30 gigabits as well in newer motherboards. So you see PCIe slots here, the latest expansion slot architecture. It was designed to be a replacement for AGP, and that is advanced graphics platform. So there's that PCIe uses the concept of lanes, i.e. point-to-point signal paths between any two PCIe components. So always then just try to see that these could be PCIe. These not could be. These are PCIe. You can we just try to put here. You just try to put here a display adapter there, right? So this is not for, mainly not used for network cards or for you know, other cards there. This is mainly used for display adapters, right? So PCIe expansion slots. PCIe pairing between cards requires a negotiation of the highest mutually supported number of lanes. The single lane or combined collection of lanes that the switch interconnects between devices is referred to as a link. Now they go down to a deep architecture here, but what they're saying in English is, because when they start talking about terminologies and maths involved, and then so it's kind of like what, really? So then you have to really understand that. So what they're saying is these these lines are interconnected with the help of those buses, and they are calling it lane 1, lane 2, lane 3 for the architecture of the motherboard. These lanes are mutually connected to each other. Now you would not see a PCI slot like this in our motherboards. Do you see, first of all, this PCI slot in the motherboard in front of you? Anyone seeing, having a motherboard where PCI slot is not there right now? So these two I am showing here. This one has it, the PCI slot. Do you agree that this one has it? Which color is that? PCI slot. White, the long one, right? Short one. So, and yeah, the short one, and yeah, this PCIe, right? So, and then, so it has it. In your motherboards, do you have that? So I see this one as well. This is also PCIe. You have this. So every motherboard you see in front of you, I think it has PCIe, right? Where the display card? Oh yeah, this one long as well. So you can see here they are referred to as PCIe. This one as well as this one, right? But why are they calling it E? Because of the speed. That's it. They're just more speedier than others, right? So the 16-bit, 32-bit, 64-bit, right? So these are the slots. They are small in size. They are long in size as well. But the main thing is, if you see the speed, you're good, right? The main thing is that you would understand that by speed. Now, this is what they are talking about. There are 7 different link weights supported by PCIe, designated X1 pronounced by 1, X2, X4, X8, X12, and X32, with X1, X4, and X16 being the most common. So the main thing is that it is all about pins. the slot has a 22 pin portion in common toward the rear of the motherboard, which you can see in the figure above. So 22 pin, these are the if you start counting there, so 22 pin in the rear of the motherboard. When you say, so you can see at the rear of the motherboard, these are those pins that you can even count in the back of the motherboard, right? And that would just show you that it is 22 pin, or is it 32 pin. It is what so 22 pin doesn't mean that it is 22 bits. Pins just are connections. This is a type, this is a manufacturer type. That's how they designed it, right? Were you able to? Because I tried to count that and then I had to count that again, because it looks much more than 22 when you see it from a distance. They looks, see this is 22. So they are, for this motherboard that they are showing here, it is saying 22 pin, right? 44 or 66? Okay, so if you have a marker, then we can, or we take a picture and then in the picture, tick, 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 we can just actually put that. So the thing is, PCIe slots, we just need to understand, is it 16-bit or 64-bit PCI? And what is the difference between PCIe and PCI X slot? 3264. No, 32-bit is this one, right? 32-bit is this one, right? PCIe, it is also being, so older name of that is, still PCIe, but we talked about PCI X. Can you tell me the difference between PCIe and PCI X? Yeah, so smaller one, this one, right? That is PCI X. And we talked about 16, 32, 32, and 64, right? So, but the PCIe also has the smaller version of their architecture as well. So don't be confused with PCI X smaller version and PCIe smaller version slots there, right? Whatever hardware they have manufactured and they say that, oh yeah, this particular hardware will fit on this particular slot, then you can just use that. Otherwise, normally you would see that empty in majority of the cases, right? Unless they have a display card that is small, the below connection area is small, and this connection type only fits here, then only you will use that. If you open majority of the motherboards, it will be populated with, this would be populated, and for network card this will be populated, right? X, normally you can, I haven't seen a lot of desktops with the smaller one being populated, but it's an option there if you have that kind of display adapter there or network adapter there, or whichever adapter you want really good speed in. You just have to order that and then put it there. So PCIe also has their smaller version, and PCI X already is the smaller version. So and you would see that they can come up with these shapes and similar cuts and call it something else, right? They would just go for the speed. Hey, we have built that speed and we are going for this name to that. But right now, PCI, PCIe, PCI X, that's what we need to remember. 16-bit, 32-bit, 64-bit, right? Nowadays it's moving towards 64-bit in terms of the slots, so we could have a real good speed there. Now there is that PCI Express. Now overall, these, when we say PCI, it will include PCIe and X as well, right? When they are overall saying that. So and this is X1. Now they were talking about the width or length. So smaller one would have a name there. I'm just showing there this, but it has a name, X1, because of the size. This size is called X1. This size is called X4. This size of slot is called X8, and this is X16. So if we say this is X8 and this is X16, do you think this motherboard has X8 or X16 PCIe slot? Seriously, I just gave it away. So, so is it the PCIe slot is X4 or X8 or X16. The shape is showing there, and shape is on the motherboard as well. You're saying X16. Anyone else? We're talking about this one. Is it X4? Okay, is it X4 first of all? Do you agree it is X4?
I can't see.
Oh, this this one.
Yeah, it's X16.
You're saying X16? Sorry. Is it X4? See the size there and see the size here. Could it be? And there are some details there, 80 Gbps, but the size of X8 and the size of X16. You can see the cut. There's a long one here, long area here, and then the cut comes, and then very small area after that, and then there is a not that long area here for this side, and then the cut, and then the small area. So which one is that? If you go for the cut, X16. So the distance of the cut and then how much is covered later. So you would just see that and you would say that it is X16, this one. Just the length of that, right? Length and width of that, right? So the thing is that it's kind of something that we need to keep seeing again and again. Normally what happens, if you don't go for a hardware job, then this is the first and last time you're hearing about this. After that, if you don't open the desktop again, gone. Whatever you practice remains there. Whatever you don't practice does not remain. So some of the students got job in Staples or in Canada Computers, and there it was cell phones and tablets and laptops more than the desktops. So they never get to see after this again. But the knowledge is crucial because though in the laptop the same components are smaller, same components. So if you know the knowledge and concept of that, you would just relate it to, okay, this is the same thing here, now this, but now I understand that, oh, processor socket is so small here, oh, the RAM is so small, 2 slots only, and the RAM in laptop and the RAM in desktop, the way you put it is totally different. Laptop, it's really small, and we're going to be talking about RAM. You will see that it's going to be totally different. You can try my laptop here, and just kidding. Okay. No.
I have a question for you.
Yes.
This is PCIe. Now, if you have a PCIe Express X1, so how you will distinguish between the two? It will be the same sizes.
So the cuts would be there, first thing, and second thing, it would, some hardware you have to go for the manual or the manufacturer. So this is by Gigabyte. This manufacturer of this motherboard is Gigabyte. That's on that chip on the heatsink. It is written.
It actually says PCIe.
Okay. If it says here, otherwise I would go for the manual. Normally I just go for manual and just download the manual from internet for this manufacturer site, and there you go. Everything is very clear. But if it says there PCIe, wow. Because for example, if I give you the the recommended way, suppose you have 4 memory sticks here. 4. There are 4 slots here. Recommended way is go for memory bank number 1. Starts always from 1, 2, 3, 4. Don't start from 4, 3, 2, 1. And when you put the RAM, suppose you have just 2 RAM. Don't put it on 1 and 3. Always go sequential. 1, 2, 3, 4. But if you put it on 4 and 3, so that might give you a problem there, right? But how do you know where is 1 starting here? Can you locate on your motherboards right now the memory bank 1, and it's written there. It's written there. Which one is 1? So are you sure the other one is not 1?
2.
It's written there. 2. Okay, there you go.
DDR1.
That is DDR. What is DDR? It is SD RAM, but we're coming for that. So are you able to locate 1 in the memory? Okay, you're able to locate. You're able to locate. Anyone else able to locate? Right beside the memory, very small, and it's the memory slots we're talking about, right? So there has to be 1 written somewhere to let you know. No, it's not on this motherboard.
Oh, it says here like the sequence. So this is 1, 2, 3, 4. Because it says here.
1. Okay, that's it. So you would look for a sequence here or a numbering here. Any way the numbering should be written there. Maybe it's not used as memory bank as a word, but numbering, right? DDR1, DDR2, DDR1, 2, 3, 4. It would be showing that way. No?
Yeah, it's XMM1, XMM2.
Yeah, it is called what?
XMM1, XMM2.
So, but how many are there? 4 or 2? So, do they only say, if they're talking about memory, there should be XMM3 and 4 as well. Try to check that. Otherwise, this is not the numbering. It's written, then this is, okay, this is for RAM. But do they show which one is 1? The first,
According to, yeah, the first one is 1, second is 2.
it could be the bottom one as 1 as well. So if I say, no, the bottom one is 1, how would you prove me that bottom one is not 1?
According to the sequence.
Exactly. According to the sequence, they are up there. Yep.
First.
Sinai. Yes. It is different for every manufacturer. They would call it memory bank 1. Some manufacturers, some would call it just A1, A2, 3. Here, XMM.
Actually, it's A1, B1, A2, B2.
And then, how many are there? 2 total or 4 total? So, do they go up to 4? A1, B3, A1, B4, like that? Because every manufacturer write something because of what they. Oh, there has to be 4. Yeah. Oh, yeah. Thank you, ma'am. Yeah, DIM A1, DIM B1, DIM A2, DIM B2. Exactly.
What's the sequence?
A's, the A's will be first together, then the B's will be together. But B's B1 has to be. Yeah. So B's B1 has to be first populated. That's why B1, B2 are showing there. But they went A1 and they went with 1, 3 and 2, 4. They went like that. So many manufacturers. So we have to really follow the manual then, and whatever some of those they will show on the motherboard. You have to really, you should have a magnifying glass basically and a torch if you're dealing with the motherboards every day, right? Magnifying glass and the torch. Otherwise, I used to open manuals and okay, there's the manual. Okay, that's this chipset and that's this. There is a thing called jumper here. Jumper is just to show. See this? There's a 2 pins connected. If I just disconnect that, this is a very small thing. It connects. It's make a connection between 2 pins there. So if you remove a jumper from somewhere on the motherboard, that functionality is not happening anymore. When you put the jumper back, suppose it was for hard disk would be connected or not connected, or display card will be enabled or not enabled, right? So you can just place the jumper back to. Many components have this jumper. So if I have put that jumper here, can you locate that jumper, which it is called jumper. It is a very small thing that really connects 2 pins together. That's it. Can you locate that, take it out from your motherboard and then put it back in? What does it do? It just makes a connection happen between the 2 pins, which in manual will show. So it's a very, very small plastic thing or cover, we can say, that would connect 2 pins together. Any 2 pins together. Yeah, you got it. Does it go off?
No, it wasn't.
Oh, it wasn't a jumper? Hey, it was a capacitor or something. We pressed the wrong buttons and it's going to.
I don't think
This
we
is
have
jumper.
it,
Can you, if you want to, yeah. So see this? I just pulled it out and the jumper is just a small cover here. Small cover. And then putting it back to the 2 pins here. 2 pins. I took it out, this one. Yeah. And are you able to locate any jumper? Okay, you're able to. Is it actually a jumper? Oh yeah, it is a jumper. Okay, got it. So this means, so terminology I'm saying, yeah, it could be green, it could be any color, but it's a plastic cover that is connecting 2 pins, which enables some function in the motherboard or disables a function in the motherboard.
Yes.
Somebody will.
Okay.
No, I
jumpers. So this means that functionality, it's optional. Okay, there's a jumper on this motherboard. Can you quickly locate that? On this one. You didn't find any?
I dropped.
Oh, you know the jumper?
Yeah.
That's a no-go area, man. That was critical thing. That man, why did you just? Oh, got it. Okay. So if you put it on the wrong pins back, suppose it was a live motherboard, it would then execute that function which was unintended, right? So you have to know with manuals where to enable one extra advanced feature and then put a jumper there. The pins will communicate at once the advanced feature will be according to the manual, whatever feature is that. So when we talk about motherboard, I used to have a shop of computers. I used to sell computers when I was young. So while doing studies, I was just doing that as well. And then there were motherboards. There was an older one, and then I have to do that and really put the jumpers. 2 or 3 motherboards were like gone because of I was learning at that time and giving computers to users. Then I would just purchase another one, and by that time I would have learned, okay, I should not be doing this. So paid from.
If you connect wrong ones in a
It's going to enable some other unintended functionality on the motherboard, and on the
actually
manual.
pen goes in any pins here.
Oh yeah, it goes to any pins. It fits. Some pins are bigger as well.
You said the jumper's task is to connect to.
2 pins and enable some functionality, because as soon as you put the jumper, what happens? The 2 pins are communicating with each other. There is some electricity current transferring from this, so they enable some function right away. And normally we used to. Yeah. So, or if you want to enable some advanced functionality here, the South Bridge would have some more chipsets enabled. If you put that jumper on these 2 pins only, suppose. So you would go to the manual and enable this chipset. Maybe the chipsets are there, but they're disabled. They're not even working. You have to enable that by putting a jumper there, right? So when we start reading on the motherboard, it goes really interesting after that. It's a whole full world here, right? It's like a planet here. But world is moving towards more software now than hardware, but that software has to be installed on top of some hardware. So knowing this really helps a lot, really. Let's just go ahead. Even in cloud, now cloud, that's where we are removed from hardware totally. Cloud is somebody else's data center, right? Microsoft Cloud, Amazon Cloud, Google Cloud. They have taken care of the hardware. We are worried about the software side of it, but that also has a virtual hardware. So virtual memory, physical memory comes here. There's a virtual memory there. Physical CPU comes here, central processing unit. There's a virtual CPU there. Network card comes here. There's a virtual network card there. So if we understand this, we understand still the software version of this as well, right? So it applies everywhere. Basically, the A plus really applies. That's why the market is crazily asking, you must have A plus to understand the hardware. So it's very critical.
Install that softwares on these hardwares.
Sorry, again?
We need to install those softwares.
For which software? Oh, the virtual hardware. So they are going to, suppose you have virtual RAM, it's going to use a physical RAM here. It totally depends and relies on the physical RAM here. Yes, they will relate exactly. It will search for where is the hardware and where is the RAM slot and how many RAM slots we have. Definitely.
In real-time scenario, it should be a supercomputer.
Exactly. Then that computer better be a very good computer. So guys, we try to relate what we are understanding from the hardware we have in front of us. There's a quick review there. The expansion bus PCI is 32 bits wide and runs at 33 megahertz. PCI X 64 bits wide and runs at 133 megahertz. To calculate the speed of a PCIe slot, use this formula: speed equals lane speed times number of lanes. Now lanes are how many of these you have here. 1, 2, 3. Some motherboards have 4 of them in server side of motherboard. Now when we say server, we understand what I'm talking about, right? We're not talking about desktop for one user. We're talking about servers for thousands of users, right? So in servers there would be long list of slots here, right? So they would also increase be an addition to the speed of whatever one network card is using. The other slots will increase the speed for that if you have more of those slots. Both PCIe and PCIe have mini versions used in laptops. So many versions of these are in laptops. I showed you one picture there, and that is okay. So the slide finishes here. This means bye bye. Let's see you next class. Just kidding. Okay, let's go for next slide now. And that is 12:12. So we don't need a break. Okay, guys. So since you don't need a break here, let's go ahead and talk about the next one. That is even more interesting. Which is just I made up a word. So so everyone's shy and they're quiet. I don't want to say that I need a break. Somebody else should say that, right? Okay, there you go. I need a break, so let's go ahead. So after that, we're talking about RAM and we're going to talk about storage. Very, very interesting and critical.
How long is the break?
The break is like 2 hours, and just kidding. So it's
Like 15 minutes or?
15 minutes exactly. So it's 12:13 now. So 12:20, 12:30. Okay, 17 minutes. So 12:30 we start. So I'm pausing this video now. Resuming in, okay, I did that numbering. So after the break, we're talking about the memory modules here, and that is, we may have seen that already in the previous class, but now it is a bit more in depth. We're going to go with the memory modules. So 30-pin SIM, 32-pin SIM, they are calling them DIMM. So singular inline memory module, SIMM would be singular inline memory module. Then it would be dual inline memory module, or DIMM. But what are these? These are memory sticks, memory modules, RAM, random access memory. So basically what happens, in fact, I should be asking you now, that when we power on, so what is RAM doing after powering on? Mm-hmm. Yes.
Operating system.
Boot the operating system and software. Yeah, and you were saying?
Well,
Loads everything on the memory. So where is the whole software sleeping? It's okay, when I do that, and it's in the camera as well here, they will like twinkle twinkle to start. I'm not doing that. So yeah, the whole data is actually saved permanently on hard disk drive. While it loads, when you power on, it loads the applications on the memory, right? So memory is bigger, the more data can be loaded. You have AutoCAD installed, you have Photoshop installed. Those are big applications, and you have like 4 GB memory. So the software might not load, or it will load really slow, right? If you have Photoshop and you have 64 GB memory, that's something that Photoshop can breathe on, right? It can load all its components, application components there on the memory. If memory is good enough, it can take and load and host all its data on that. So when we power off, what happens? The reverse is, so the whole data that is loaded on the memory is back again loaded to the hard disk, right? So hard disk is where it stays there forever if you don't delete that, and memory is where it loads as long as the computer is powered on. So first, when you power on, obviously the operating system files will load. Operating system means Windows Server 2016, Windows Server 2012, Windows 7, Windows 8, Windows 10, Linux. Any Linux guru here? Guru means expert. Any Linux? Okay, so Linux operating system. So whatever operating system is there, it loads first, and then applications on top of that load as well on the memory, and then it works. If memory is full and you still keep on double clicking on MS Word, I want 10 instances of MS Word, Excel, PowerPoint, and then on top of that I'm opening Photoshop, which is a big application itself. Then it might run out of memory. It will use some of the portion of the disk, and that portion of the disk that is used as the memory is called page file. We talked about that at the start of the class. So when the memory is loaded, it's really working hard. All the applications are loaded there. it needs some of the space of the hard disk as to be used as a memory. That is in Linux called swap file. In Microsoft it is called page file, right? So the portion of the hard disk that is used as a memory, right? But in Linux it is called swap file. That you also need to know. Okay, so we're talking about the singular inline memory module and dual inline memory module. Then there is a SODIMM here as well, and we may remember, so these are larger, longer memory sticks there. Now this 30 pin is, you if you see that, just hang on to it for 20 more years and you might sell it in $1 million because it's museum stuff now. So but 30 pin, otherwise 72 pin and 168 pin, especially 168 pin is very common now on the motherboards anywhere. Maybe you have some memory sticks there. Oh, none of them have it, really? Okay, then. Oh, thank you. So yeah, that's a memory stick, and I think both of you did not put it there. So again, just quickly, because we're going to do that, talk about memory. So you can see the cut here, and you can see the cut here. Make sure they all are together. And second thing is, see this? These are the clamps, like this, right? So when you are putting it right above the cut, just put some weight on it, and the clamps should just automatically be contracted there, collapsing there. So you might want to start that and try to put on the first one, not the second or third one, which is, we already practiced that, which one is the first one, right? And different motherboards have different terminology. A1, A2, A3, or memory bank 1, 2, 3, or yeah, you can just put it there, yeah, and just give it a little push now. No, just kidding. Yeah, give it a push. No, really, good push now. Oh yeah, just put some good, yeah, there you go, smooth. Now you have to take it out as well. How to carefully take it out? Yes. There you go. See, okay. So you should be doing it with eyes closed. You cannot see that, just kidding. Okay, so and in the next at the end of the course you will all be doing that with eyes closed and hands behind the back,
So how are you supposed to?
because you did it so many times. It should be very easy for you now, right? Okay. So SODIMM is used for, okay, SODIMM is used for laptop. Is that correct? So you can see the size of it and you can try to figure out, but obviously we're going to see that, we're going to try it as well. But 168 pin DIMM or 72 pin DIMM, you can see the sizes of those RAM sticks, and then you can see the size of this one. So if it's a DIMM SIM, it is for desktop. If it is so DIMM, it is, and you can see the size, it's for laptops. So we should be very clear, laptop RAM and desktop RAM. Desktop RAM, obviously the size is bigger because desktop is big, right? Laptops are smaller. Hence, that is, this RAM has to be smaller as well, right? So DIMM, so DIMM, right? Two things. Let's go ahead and try to understand what are these, why there are chipsets there, why there are fewer chipsets. Laptops, DIMM or SIM. It's going to be, nowadays it's going to be only DIMM that you will see, but SIMs were also there. Now about this RAM, you have that? Oh, so thank you, ma'am. Thank you, ma'am. Okay, the chipsets are on two sides here. Chipset here and chipset here, right? So there used to be memory sticks which had just chipsets on one side, but the other side was just clear, right? So SIM is where the chipsets are only on one side. DIMM is where the chipsets are on this side and chipsets are on this side. This means the memory is doing double work. The more chipsets, the more work can be taken from, more applications can be loaded here if more chipsets are available there. Chipset here, chipset here. Some gaming laptops have and desktops, especially gaming desktops, have memory that have or RAM sticks or memory sticks which have actual heatsink on top of that. The memory has a heat sink because it has a chipset that's going to work really hard. that's gonna heat up. So it has to have heat sink. I haven't seen a fan on the top of memory, but heat sink is pretty common for some of the RAM and where there's a gaming laptop. So if I just go for memory stick here, okay, there you go. So dual inline memory module, it has chips on both sides, so it performs double work than same single inline memory module, right? So you can see if it's on the, and you will see pretty much nowadays every RAM as DIMM. It will be chipsets on this side, it will be chipsets on this side. This means it's just performing more double than if the chipsets were on one side, right? So that's why it's called DIMM, because it has chipsets on both sides. I'm gonna ask in next class this reason. And if there are any questions till now, time up. Okay, let's go ahead. No, but there's no never time up. You can ask any question anytime, right? But remember that it's DIMM, and then let's go for just some more options there, and you know how to put them, and you know it has to be put on the first slot, RAM slot there, right? Not the third or the fourth. Now, Sinai actually pointed out one thing, or he was asking that. It was a very good question. Some of the boards in server side as well, that some of the boards are okay. Oh, in fact, four slots. Yeah, that's two slots. Can you think about? Okay, so here some of the boards have that you have to put a memory on 1 and 3 and then 2 and 4. It's like that. Some of the boards go that way actually, right? So that is more common in server side. That 1 3, so you cannot then put 1 2. Then you cannot actually. It's gonna give you error, right? 1 3 2 4. You can go this way.
How we would know?
Or it would be written in the manual first thing, and in the server side, it's the manual is actually created in the that you know, when you open the cover, inside the cover, it clearly gives that how will you put the RAM. First put 1, then put 3, then put 5, then put 7, and they have 8 or 12 slots. Servers, thousands of users will be connecting to that, right? So and one of the motherboard, maybe this or that other one, that it was A1, then A3, then it was B1 and B4, right? Or A1 and yeah, yes ma'am.
If there is no manual, how you can search for the manual online?
Then you just put it 2 ways, better search online and then do that.
Okay, how you search for the motherboard? Which information you need to
Oh.
find?
So there is ATI written there. Some we're lucky that it's written there right now. Otherwise, in the background, I would just try to check the model serial. This is just a serial number, but it doesn't say any company.
So you
So
put the serial number and you search for
yeah,
the manual?
or there's a wider or more amount of chipsets are showing VIA written there. More amount of chipsets are showing VIA, VIA. I would try to have a lead on that. If this information is not enough, then good luck. Then then it's not that easy. So when we buy it, obviously we need to stick to that
But
documentation.
maybe you are working on
Yes.
someone else's computer and they just throw the manual because they don't know what is it. Or
Then-
like you bought a used computer, so there's a
And that's where good luck. Yeah, I mean, like this is the only helping point. So whatever we see is what we can get help from. It has one socket, but million other motherboards have one socket as well. And it has 4 RAM slots. Million other motherboards have same thing. 3 of
so you
these,
can't distinguish
no.
without the manual.
It's like too many of these. If we don't have some specifics written there, no way. Some other boards, it happened to me that I had to search and I couldn't find it. Then whatever experience I had, I just operated according to that, and it worked. But yes, that's a good question. I already know. So if this is all we have, then we're pretty much good luck. So. But if you want to know that the memory, how it's done, so we went through that, and yes, you have to really follow that. I mean, like if you can find it, memory bank 1234 or 134 or 24, that needs to be first seen before we actually do that for our friend's PC, or just hope that the friend is a very good friend. No, okay, because when the PC is gone, okay,
So it will go.
no, it's not gonna work. No, it's.
Like, can I try?
Suppose
Try
it's
and error?
sequential. Yeah, suppose it's sequential 1 2 3 4, and you put 1 3 4 2 4. It works still, recommendation is go this way, but it's going to either give you an error after some time, or it's going to perform slower. Most probably it is perform slower, because it is not communicating that way. It is supposed to communicate 1 3 2 4. It's going to communicate that way. It's not going to communicate with each other in 1 2 3 4 sequence, right? So the performance will be not that good while you paid for what you're not getting that. So here, if you go for memory modules, differ in the number of conductors or pins that each particular physical form factor uses. When we say the term form factor, it's just another word for architecture, right? Form factor, how does it look like, where, how the chipsets are shaped, how far the chipsets are, how many chipsets are there. So I could show you a lot of memory sticks where there are even more chipsets than this one. So it has a proper distance between all the chipsets here, but there are many modules that have bigger chipsets, and they are more in number. So this means it's even better in performance, right? So more chipsets, the definite. And laptop memory comes in smaller form factors or architecture known as small outline. So is small outline, and then the DIMM is dual inline memory module. So and micro DIMM. So it is SODIMM and micro DIMM. These are for laptops. Obviously, they will be smaller, right? The single inline memory module is an older memory form factor that began the trend of placing memory chips on modules. So you won't see SIMs a lot. DIMMs are common in PC. Suppose you have 486, maybe you've heard that term before. It used to be 386 processors and 486 processors, then 586, then came Intel i3, i5, i7. Nowadays it's i3, i5, i7. So this is i7, and others could be others as well. And yeah, all my students in other courses, they'll be passing by, and I'm not doing this. Okay. So then there are memory slot characteristics here, SDR, and then we're going to talk about what is this. But SDR, SDRAM, 168 pins, 184 pins, it starts from that. So in previous diagram we talked about this, that it is 168 pins and this is the shape, but within this shape now comes more pins there, 240 pins there for DDR2 SDRAM and DDR3 SDRAM. So this is where this is what we are using normally now, DDR3 or DDR2. So in i3, i5 computers, those computers that have processor of i3 and i5, you would have Intel i3, i5. So it will be DDR2, and i7 quad core is DDR3. DDR3 normally goes for 32 GB RAM, so capacity is more. That's what normally it is. That DDR3 is it goes maximum up to 32 GB, and DDR2 goes up to 16 GB. So your laptops at home would be mainly DDR2 if they go maximum up to 16 GB RAM, and DDR3 RAM can be placed there if it is maximum go up to 30 GB RAM.
What about DDR and SDR?
SDR are not there anymore, or if you have very old desktops or laptops. Very old would be like 6-7 years ago, or even older than that. Yeah.
What about DDR?
So DDR would not be there as well now. In desktops you would find that, and that would be 8 GB maximum RAM. So 8 GB is nowadays, even for basics it is not enough now. Some laptop students do bring, and I say that get a good hardware first if you want to stay in the field of IT. So you should have a powerful laptop or desktop with i7 quad core processor, 32 GB RAM, and 500 GB minimum SSD drive. Fast. You can create big networks there. VMware is a virtualization course. You have to do that. It creates a lot of, it needs a lot of processing and RAM, right? So, but we're talking about this 240 pins. So there are those. It's going to touch a pin there on the motherboard here. So this is the capacity there for 240 or 168 that we are talking about here. Now you can see SDRAM. S means synchronous. It means it is synchronized to the system clock. System clock and this are synchronized, which means that the way processor processes in that speed, this is the same speed, the RAM should be also updating its data to the processor, right? The speed with which the processor is running all the commands there, the data from the RAM should be coming from the RAM. The data should be with the same speed. Synchronous and asynchronous we talked about. Synchronous is real fast. At the same time, it is loaded on memory. At the same time, actually, the processor says that, hey, load on the memory. At once it goes there, loads the data on the memory. So memory and processor should be in sync. When I say in sync, what does that mean? They should be working on the same speed and should be synchronized with each other. Whatever's happening here right away should be happening there as well. Should be updated there. Yes, sir. Within asynchronization is for longer distances.
So can that also be used for RAM or no?
No way. Then it will be really slow. So asynchronized replication normally are used in SQL servers, more applications where there's a distance. Even in SQL servers, in LAN, you will have synchronous replication. But in WAN, between on the internet, you will have asynchronous. Or wherever you don't need data right away. But normally in LAN, or this is what we're talking about, intercomponent communication now. That has to be synchronous. Otherwise, no, asynchronous is not even like kind of possible. So you can see the RAM here. There are chipsets here, and then you can see that this is a big heat sink on top of the chipsets. Obviously would be there under it, but you can see a big heat sink on top of that. So this means this RAM is expected to perform a lot, and in turn it will create a lot of heat, and that has to be absorbed by this heat sink, right? So this is how it looks like, the RAM with a heat sink and RAM without a heat sink. But if it, suppose it heats up a lot, so what? What's the big deal with that? It would fry, and I definitely like fried eggs, but fried RAM, no, I never tried that. So fry means that it will not work. Definitely it will just simply cease to work. So SDRAM, S means synchronous, and then there is that it's synchronous with the system clock. When we go for that, a double data rate SDRAM or DDR SDRAM, 184 pin, 2 notches or 2 cuts, you can see. 1 cut here and 1 cut here, 1 cut here, 1 cut here, right? SDRAM. So what it is just it used to be the DDR or double data rate. DDR means double data rate. It's just for speed they're talking about, and it used to be 184 pins, and you can see the difference between this RAM having 1 cut and this RAM having 1 and 2 cuts here, right? So older RAM would have 2 cuts, but you know, even the latest RAM, they could just put 3 cuts there. It's up to them. We just need to once see and identify it. Okay, this is how they introduce it, and then we know it, right? But it's not like older RAM will have 2 cuts, so it has to be necessary that new RAM will have 1 cut. But pretty much nowadays what you see is 1 cut RAM. They could create another cut just for any other reason, right? So we see that DDR, SDRAM is there, but this is something that we don't use now. It's 240 pin normally we use nowadays. This is old, but we should know how older look like. And so many of my friends have older computers there. Whenever there's a problem, they just tend to call me or ask me what to do there. And I tend to not visit at that time, because if I restart something, suppose I take out the RAM and put it back and it doesn't start, then they will say, whoa, what did you do? It's all your fault now. Okay, really? So there has to be a big disclaimer that I put there. And if it's also that spicy rice called biryani and samosa, I don't, maybe you guys don't know that what I'm talking about right now. Ever heard of biryani before? Okay, there's a yes. Yes? Yes? No? You hurt my feelings now. Okay. Spicy rice. Yeah. So you will see a lot of reference of food, right? And I really want to become smart as well. So 2 addictions: being smart and loving food. Seriously, what's wrong with me? So anyway, let's go ahead. Now DDR2 240 pin, that's the standard now, and you would see here notch is in different place than the DDR. So the cut here was there in the previous RAM, and now it is here, and that's pretty much what we have here. and that is DDR2. So this RAM, which is not being used right now, I think it's fried already. So the thing is that the cut is here. This means it's a DDR2 RAM. It has 240 pin right now. It's a DIMM because chipsets on both sides. Exactly, chipsets on both sides means double work, means a lot of more applications. Now the demand of applications have also increased. You buy an operating system, it needs more than 4 GB RAM, right? So basically you can't afford to have a 2 GB RAM and work with today's applications. They need more RAM. They're just hungrier for RAM, processing, and fast hard disk. So faster the better, right? So all these components have to be faster, right? So, and when you go to server side, it's even, worse than that. I mean, like, you cannot afford to have a lag in performance. You can't afford to have a lag in performance for a minute. Some companies might lose millions of dollars if there's a downtime for just 1 hour, 2 hour. Hourly, they are losing hundreds of thousands of dollars if there's a downtime for their some critical applications. So hardware has to be very, very reliable, and there has to be two hardware or three hardware where a active application there and its copies are running on the other hardware, right? That's where actually the companies really want your skills. That can you make any application highly available and keep it that way, right? You keep the business running. That is also called BC, right? British Columbia. No, business continuity. Business continuity is that business must not go down even if your two servers crashed and there was a critical application out that the third, fourth, fifth, sixth servers should be still running that same application, right? Can you do that? So we, in fact, Sunday class was morning class was MCSA first course 70-740. Its seventh class was there, and we actually practiced a feature called failover clustering. Failover clustering is you have two servers there and application is in both servers. One is active, one is passive. And then next Sunday, we're going to do the part 2 of that, and we're going to crash one application. I'm going to prove that, hey, that service on top of that is still working while we crash the underlying hardware for that. So that crash test will prove your skills. How can you implement failover clustering? So that's where you should be going. That's where 35, 40, 50 per hour jobs are, right? You need to know disaster recovery, backup, high availability, right? In all applications. Monitoring software will tell you right away. And if it crashes, it should automatically move. We don't have time to interfere at all. It should automatically be just highly available. But the way we configure it is what the skills they need. Okay, so DDR2 240 pin DIMM notch is in different place than the DDR. We get that. Okay, that's a newer one. It's 240 pin. Obviously, it's DIMM, so it's two-side chipsets there. So it's pretty much faster than the previous one. We get that. So then there's DDR3 and 240 pin DIMM notch is on a different side yet. So there's the notches here for DDR3. If I go for DDR2, the notch is here. The cut, as I was referring to, cut here is here, and cut, it's like it looks like could be very near to the or same, but they are on different places, right?
So not all of them can fit.
Yes, that's the point. Purchase another board for that. Thank you very much. Make us rich. Yeah.
They are not compatible.
No. So DDR2 cannot be placed on a motherboard with DDR3. DDR cannot be compatible with DDR2 and 3 compatible motherboards. So you have to purchase a full new motherboard for that. So that's why, yeah, if you want to upgrade, you upgrade the motherboard and processor first. Then you put, or you don't have to upgrade hard disk, you don't have to upgrade, but for the RAM, motherboard, processor, these are 3 things you have to upgrade if you want to go for better speeds there. So notch is on different place, so we cannot mistakenly put DDR3 in a DDR2 supporting motherboard. We get that, right? It can only fit one way, that there's no other way to fit it, right? And you can see that there's a heatsink on top of, we can't see the chipsets now, so the heatsink is on top. We get that, okay, this must be some good performing RAM there that's gonna heat up. So we understand DDR3 240 pin, DDR2 240 pin, but the notch or cuts are on different places, and DDR 184 pin, which is not used anymore, but DDR2 and 3 are being used, and they're not compatible with each other. So you have to upgrade the whole motherboard for that if you want DDR3. Now there is DDR4 there also coming. Maybe it's already there, and it obviously its cut is also different, but it supports up to 64 GB RAM. 64 GB RAM is wow for a desktop here. So DDR3 goes maximum up to 32 GB RAM. So normally on day one I tell the students, hey, purchase a new refurbished laptop. I also have this refurbished laptop, and on Kijiji you can find that, right, or eBay. But this laptop is a new one would be $25 or $3,000. This one is 900 or 1,000, but it's a one-time investment, and then you can install all the applications, enterprise applications, create your own environment in this laptop. But in order to survive in the field of IT, plan to purchase a good hardware, right? Otherwise, it's not easy. I do AWS cloud classes. There we have some machines that we download, virtual machines, which require 16 GB RAM. So you must have first 32 GB RAM to give that 16 GB RAM, right? So whichever course you're doing, you would need, if you have a hardware of your own which is powerful, you can practice a lot. And so whichever field in IT, you would need a good hardware. Okay, so we understand the DDR1, 2, 3 here, and the 240 pin and the chipsets. And then comes example of memory, where else memory is used. In processor we talked about L1, L2, L3 cache. These are basically memories, and you can see the size there. L1 cache is just 64 KB, 256 KB is L2, L3 is 4 megabyte to 12 megabyte. So it's just queuing the task, and that's it. Go, go, go. Come, new task, go. And task itself is a very small data that the processor needs to execute and get the details of. RAM can go up to 4 GB. Now this is a pretty old slide. RAM can go up to 1 terabyte as well. 16 GB is like what? Okay. HDD and hard disk can go up to terabytes, obviously, and exabytes and petabytes as well.
You said RAM can go up to a terabyte?
Yeah, 1 terabyte RAM.
How?
Maybe 5. So it's just like a stick, or maybe it's 512 GB, 512 GB. This is like what, a 4 GB stick, 6 GB or 16 GB. My laptop has 32 GB. Maximum it goes. That's it. And 32 GB is what? $500, $300-400.
How much is
1 terabyte would be then few $1,000s, $4,000-5,000.
So that's only for server.
Only for server. Servers can go up to 200 GB. This desktop and laptop can go up to 32 GB or maybe 64. There are servers that can go up to 200, 300, 400, 500 GB as well. Servers, because thousands of users are connecting there. That's why.
There's a lot of applications.
Yeah, a lot of applications, or one big application. Suppose it's a hospital. All the doctors and patient records, nurses, they are connecting to one application there. So that application has to be on top of a very good hardware. Okay, so we're talking about the use of the RAM there, and then cache memory resides between the CPU and RAM and enhances the speed of the system and not the amount of RAM. Then we talk about cache improves system performance by predicting what the CPU will ask for next and prefetching this information before ask. So these are those tasks that you are double clicking so quick, and processor has to perform those and execute those tasks, so cache really caches them, right? That's what we talked about before as well. So level 2 cache resides on the motherboard, hence also referred as external cache. Level 1 resides on the processor on its die or silicon wafer. Wow. And for this reason is known as internal cache. L3 cache is when the extra space on a processor packaging is used to bring L2 cache from the motherboard to the CPU. Now in English, what it means is what I saw, what I showed you here. Locate that cache, right? So there was in the middle of the processor, the cache was there as well, and then there are sides of the processor, or external cache is there as well. But then there is internal cache as well, which still works as a cache on its die or the silicon wafer. The socket. So it would be, if I just show you a cache, one example of a cache here as well, and that would be either a US dollar or a Canadian dollar. No, that not that example of cache. So it would be a cache or L2 cache processor, and I should have put a hardware there. So they do. Oh, what happened to the network? So yeah, CPU and second cache. Well, that is one example. We can physically try to see that. So there are outside cache here, and then there's a in the middle of the processor there's a part of the processor as well. There's cache. So L1 cache would be that within as part of the processor, but the other caches are there. Normally they are saying that for a very older computers there, but you would see this those what I have showed you there as the cache, and I can sometimes the pictures show up and sometimes it they don't show up. Yeah, see this? So we're talking about the silverish cylindrical shape. So these are those caches there, right? So now what we are talking about here was L1, L2, L3 cache. We talked about in fact that already. If I just go ahead, when the extra space on a processor packaging is used to bring L2 cache from the motherboard to the CPU on its packaging and not die, it's referred to as L3 cache. But overall, the purpose is it's part of the processor, it's near the processor, and they are queuing up or prefetching the task what they are about to ask next. So caching that information, and when the processor asks that, it just executes that, right? Now, quick review here: RAM, sticks, and speeds. To do anything on your PC, a program must be loaded onto RAM. So that's what we talked about. As soon as you power on, whatever software was sleeping in the hard disk, it wakes up. Okay, okay, we have to go to work. Go to work means load on the RAM, and it loads on the RAM. And after that, whatever you're seeing in front of you, this is all loaded on the RAM right now, right? And if I can just load a lot of other things in the background, Word, Excel, PowerPoint, Access, YouTube, 10 videos together. So if I have enough RAM there, it's going to keep on loading there now. New processes, new requests there, right? So DRAM and SDRAM were earlier slower forms of RAM. Modern RAM comes in DDR, DDR2, DDR3 varieties, right? So this is what we were talking about. RAM capacity, quick review. RAM capacity is make sure your motherboard can handle the amount of RAM you want to install. So if I talked about that RAM DDR, so you already know, first of all, the shape will be different. It will be not compatible with other motherboards, but also the capacity as well. Your DDR supported motherboard can go up to 8 GB RAM, DDR2 can go up to 16 GB RAM, and DDR3 go up to
64.
DDR3 is
32.
32, DDR4 is 64, which is upcoming hardware. Maybe in 10 years, our kids will be having DDR4 RAM, which will be 64 GB. It's already in the market, but it's expensive. Okay, so RAM capacities are additive. If you install 2 GB sticks, you have 4 GB of RAM. So minimum, it's one stick could go 2 GB. It could be one stick 4 GB. It could be one stick 8 GB and 16 GB, right? So I got the laptop with the 8 GB RAM. Then I went to Canada Computers and asked them, then can you make it 32? So, but they said the price, and that then I said, okay, make it 24 GB RAM for now. So they just added 8 GB more. So I had 8 GB before. I just added 8 GB more. Then I went later. Then okay, give me 8 GB more, so make it 32 GB now, right? So one 8 GB, second 8 GB, third 8 GB, fourth 8 GB. You just go like that, or 1616. But if you want to go 1616, it's not in DDR3. You have to upgrade the motherboard and put it as DDR4. The motherboard that supports DDR4 RAM, and the cut will still be different, right? DDR3 will not be placed on DDR4 compatible motherboard, and that will go to 64 GB, which is wow. Okay.
Will you be able to change the motherboard on the laptop?
No. I was gonna say yeah, no. Desktop, I thought you were gonna say in the end, but it's laptop, no. Well, physically yes, technically we can. It's just that it's not worth it in terms of money. You can actually go for with that kind of money. And yes, the laptop's shape is strict. So a motherboard for DDR4, does it fit on this laptop? So if the company is making that, yes. For desktops, they make it all sizes, so yes, you can. But laptop, not a lot of examples there.
Can you change the processor on the laptop?
Yes. You have to check the, suppose you go to the laptop, so this is ThinkPad W540 Lenovo. I would go to the website and I would just check that, okay, exactly this model W540, this motherboard supports what kind of processors. I have 1.2 two processors there, 1.2 gigahertz. So maybe that motherboard says that it goes up to 3.6 gigahertz as well. So I can, yes, I can order a 3.6 gigahertz processor. That would take my applications, it'll be really fast. It will be wow. Right now it's 1.5 and it's okay for me. 3.6 would be like wow. It will be opening very big applications very fast, right? So yes, motherboards need to be known if they support up to what processor. And I think I'm on the initial levels there, 1.6. Yeah, you're okay with the fan? Fan is okay. Fan is okay. Yeah, just sometimes it goes so fast then we are blown away as well, right? So yes, so stick to your seats and seat belts if you have them. Just okay. Yeah. So here, avoid mixing RAM sizes and speeds. It can cause stability issues. Stability issues is one thing. If it is 1324, don't go for 1234, right? So the RAM, it's going for mixing RAM sizes and speeds. Now, sizes and speeds also means this is not talking about sequence actually. This is talking about sizes and speeds. So I got two 88 GB Kingston company RAM. Then I got another 88 GB. Kingston was not available. Kingston is one of the best ones, right? So I went for another company. I don't know which company was that, and I put those, and yeah, my Windows crashed after that. But the same thing happened with my friends. They had different two RAMs for different company and two RAMs for different. It worked fine. So and suppose you have 8 GB. Suppose you have 2 GB and then 8 you're putting. So they're saying don't do that too. 8 or 2 try to do that, but it works. Like now you have 2 and you have 8 it pretty much works, and different companies also work fine. It just happened maybe that one time to me, but when you do it you understand that right away, right? So they say recommendation is Kingston RAM, just buy 4 if you are going for 4, or just look for Kingston then. But that's not hard and fast rule. It works with any other RAM. Come on, if you don't have Kingston, what do you do then? Right? You have to put some other RAM. So in fact, my laptop has 2 from Kingston and 2 from some other company, and you're working fine, right? Yeah, good. Says good. Okay, so here we're talking about different sizes and different speeds. It's not talking about sequence, but sequence has to be followed, and we can follow it from the motherboard. It's written on the motherboard. That is important enough for us, because it's written, it's mentioned on the motherboard how it is a 1324 or 1234. Okay, so small outline dim or SODIMM. This is how SODIMM looks like. Now you can see that chipset is only 4, right? It's but chipsets may be bigger, thicker. It's just that the performance is exactly the same. So if this desktop supports 32 GB RAM and this laptop supports 32 GB RAM, the performance should be the same. It's just smaller in size, that laptop memory. Laptop RAM, SODIMM, small outline, dim. They also are DDR, DDR2, DDR3, but it's all in smaller size. That's the only thing. They perform exactly the same, right? So if we go for that, RAM bus RAM was the first double data rate RAM. It used to be called RAM bus, that is just and then ECC and parity RAM are special varieties of RAM often used in server machines to increase stability. Now these are the types and architectures that were used in server. SODIMM RAM is used in laptop, PCs, and comes in several varieties and capacities. All RAMs comes in several varieties and capacities, so it is same for the laptop as well. Whoa. So memory inside. Can you know where the memory is? Seriously, what kind of question is that? It shows it. So, so they have placed that memory there, here, there, and you guys all actually did that, so you know where to put the memory there, right? And which one is a processor here? Okay, that was easy. And I haven't talked about that. What are these cables? These all. No, they are cables. So buses are built into the. They are actually part of the motherboard. But did that course before. That's not fair. Yes, they're ID cable. How do you know that? IDE cables. Now we're going towards that topic now. I shown you the hard disk cable that is smaller in size, that is called SATA cable. Before that, this used to be the case. IDE cable used to be there. So somebody knows everything and is pretending not knowing. Oh, okay. So,
I
so
studied all of that, but I don't remember.
okay. Now coming back, everything is coming. That's very good. Okay, so memory characteristics. There are. This is what I put the that. Oh, seriously. So we're talking about parity check, cells, memory banks, error correcting code, single and double-sided memory. Now it counts, right? So single, dual, and triple channel memory, and then buffered and unbuffered memory. So if you wanted to catch up with that sleep, now is a good time. Don't do that. I'm just kidding. So no, it's just that I'm so worried that Timbits are way further, with that, the guy who loves Timbits. I mean, he loves Timbits. He's gonna finish all of them. So I'm just worried about that. That's genuine worry here. Hey, you didn't even get the joke, right? You were supposed to smile right now. You were supposed to smile. You just hurt my feelings. Oh, just okay. So yeah, let's go ahead. Parity checking. Now, if we go for that, parity checking is a rudimentary error checking scheme that offers no error correction. So there's a checking, there is a correction. So parity checking is all about error checking and reporting, but not correcting it, right? So memory nowadays have error checking plus correcting as well. It used to be just parity checking, and then error would just pop up. Hey, I told you so. So and bit is the smallest unit of memory. Memory has its own management part as well, where its management data is there that is doing all the checking, right? So when every application loads in the memory, so there is that small software that also loads that is supposed to be checking within the memory chipset. That part is there within the memory chipsets, right? So this chipset would has a software there, right? This chipset would have a software inside that would be really running. So they have to put some software there for receiving all the data there. The rest of that applications are loading on those chipsets, but there is also part of that which is managing the memory as well. There is no separate application we install. There is no separate utility we install. It's built within the chipsets. It's available, right?
So what kind of error we can expect and what it is to correct?
Yeah. So errors can come any type. For example, error will come if you have loaded all that data and the memory cannot take it. So either it will give you an error, memory cannot take. So you have loaded so much data, so it will just not load any data. It will give you an error right away. That hey, there is no space there, and you're loading that. Then there are that when you're loading data, some data may be corrupted. It's not loaded in an organized manner. It's going to give an error, right? So there are many ways that the error could occur when applications are loaded, and normally it's a corruption of the memory itself as well. It may not be flowing, but normally mostly it is when too much data is there or corrupted data is there, right? Or all of a sudden there's so much request coming, you overloaded that, so the data will, or maybe it is a physical problem, maybe the heatsink is not working, it is too much heated here, so it will give you error as well. But that is a physical error.
But how to correct the error, how many times it will
Whenever
report
the
the error,
Mhm.
how many times it will retry and then how it corrects.
Oh yeah, it will keep on retrying until the error is corrected, or it will say, I give up, I cannot do that. There is no specifics of that.
Limits.
Only 3 times it will try. It will keep on trying if it cannot do that. So there has to be a number of times, but it normally tries, and then gives up. Okay, I cannot do that, right? So, yeah, you were saying? Okay. So bit, smallest unit of memory, it's like an atom. It's either a 0 or a 1. Okay, going down to bits. And then byte, group of 8 bits, e.g. 0, 1, 0. So these are 8 bits where one character is fitting in. 1 byte can store one letter, for example, A or Z, right? So bit and bytes, we may have heard about that before, obviously. And there's a byte when you byte 10 bit as well, right? So, just kidding. Okay, so then there's a kilobyte, so 1000 bytes, megabytes, thousand bytes, gigabytes, 1 billion, terabytes, 1 trillion, right? And then just byte. So anyway, parity checking works most often on a byte level or 8 bits of data. A ninth bit is added at the transmitting end and removed at the receiving end so that it does not affect the actual data transmitted. So the main thing is ninth bit is added there and it is trying to load that software there for the error correction. If receiving end does not agree with the parity set in a particular byte, parity error results. Now there is this way the result can happen or error can happen, and there are other ways like if the memory is not performing or maybe the application is not performing, maybe the application is corrupt. That is also a way. So for parity schemes, even and odd for systems that compute parity, and mark digital pulse or 1 bit and space lack of pulse 0 bit for systems that use non-parity. So basically what in English it is saying is that this was also English, but it's kind of when you start reading that, it's like, whoa, what okay. So the main thing about this is that it will try to do error correction as soon as it discovers that it says that it works on a byte or 8 bits. A ninth bit is added at the transmitting end and removed at the receiving end so that it does not affect the actual data transmitted. So whatever data is being transmitted, it just checks every data there, that is there any error or not. If receiving end does not agree with the parity set in a particular byte, parity error results. So if all the data is not received there in 8 bits, or if there's a corruption in the data in the 8 bits coming, then it will create an error. It will report that only. Yeah.
Can you explain parity checking one more time?
Parity checking is error correction, error checking only. Sorry. So parity checking will be checking of errors, but not correcting them. There's another feature coming that will actually make the correction, and that was the one that is the one that is being used now in memory.
So it's
So
not going to be correcting errors
no,
with regards
it is detecting
well, this is with regards to what is it checking?
applications. So when it loads 1 byte, that 1 byte is the application. Suppose when you open MS Word, it might take maybe 1 megabyte or 20 megabyte to load. So that data is going to the memory, 20 megabytes. So it's saying that it is checking one byte there or 8 bits, and it is checking every byte if there is any error coming there or not
So
within that byte.
This is on the RAM.
Yeah, that is all happening on the RAM. Exactly. So that's what it's saying, right? So error checking or detection, but not correction. That's the main thing. First thing it's saying. Second thing is it's checking in 1 byte, each byte. And suppose you're loading data that is megabytes or gigabytes, so amount of work that you can imagine it is doing it within seconds is amazing. So then there is the most basic implementation of memory is 8 chips to form a set. Each chip has millions or billions of bits of information, each in its own cell. So 8 chipset. Now how much are these exactly? If I see that 4 here, so 8 here and 8 here. Basically a memory comes with 8 chips. It's 8 chipsets, right? So 8 chips on this side you can see now, 8 chips on this side you can see now, right? 8, they're 8, right? Or maybe I've eaten less Timbits, so they're 9 here. No, they're 8, right? I'm referring to Timbits so much, and nobody had gave me the box there. So no, I was just looking at Avas all this time that he's so brutal. He's looking at teacher that teacher is asking for Timbits and he's not giving.
And you're the only one who's talking, and I think you're the most tired one. You're just listening. Like,
But here you go. Since you needed it,
yeah.
I'm giving it back. Just kidding. Yeah. So yeah, the education has to be fun. Yeah. So that's why we're having.
Have some energy.
Okay, energy and some sugar. Yeah. Okay. So sometimes there's not a many classes. Sometimes there are CEOs and directors and managers coming there, and they are used to my making jokes. So one day they were like doing this, and I was okay, guys. So it is, and I'm talking about the most important topic now in cloud, and they're like, "Whoa, what happened?" And they were looking at each other. Then, really, you do these kind of jokes as well? Then they say, okay, yeah, just bring it on now. Now we're gonna be ready for anything. Mhm. Oh God, this got recorded. Okay, anyway, uh, yeah, I have to really edit that, but I don't have time for that. Okay, so you have to bear with this as well. Now, for every byte in memory, one bit is stored in each of the 8 chips. So, where's that? So, in the chipset, you have every byte in memory. So, normally there is 1 byte, second byte, third byte, and the parity is checking error on each byte. So, 1 bit for 1 byte is placed on this chipset there. A ninth chip is added to the set to support the parity bit in systems that require it. So, suppose if there is ninth bit needed to be added, they add an extra chipset for that. Now it is 8, but it doesn't have 9 chipsets there. One or more of these sets, implemented as individual chips or as chips mounted on a memory module, form a memory bank. So, one or more of these sets, implemented as individual chips or as chips mounted on a memory module. Normally, you would see in a Canada computers when you say, I need a RAM, so and can you put it on my desktop? So you take the desktop, suppose. So they would say, oh yeah, I'm putting that in memory bank. They would also always refer it memory bank. So these are memory banks where you put the slot. RAM slot, you can say here, this, or memory banks, right? As well, you can refer to that as well. And then the next step in the evolution of memory error detection is known as error correcting code. This is called ECC. Previous one, memory error detection. So this is evolution, right? So the next is the error correcting code, ECC. ECC can detect single and double bit errors and actually correct single bit. So double bit errors, or single bit would be in 1 byte there are 8 bits. So 1 bit has some corruption there, it can detect and correct that. 2 bits have errors there, so that's within 8 bits, 2 bits have error. Second bit or multiple bit it cannot correct. So errors, in other words, if a particular byte group of 8 bits contains errors in 2 of the 8 bits, then ECC can recognize the error, right? If only one of the 8 bits is in error, ECC can correct the error as well. So it has some limitation to correcting the error, but it will detect the multiple bits error as well. Commonly speaking, the terms single-sided memory and double-sided memory refer to how some memory modules have chips on one side while others have chips on the both sides. So we talked about that already. Double-sided are DIMM and single-sided are same. Double-sided memory allows more memory to be inserted into a computer. Okay, we get that. So, two things. Parity back there was that it will detect the error, and then ECC would be, error correcting code would be that it will correct 1 bit if there's error on 1 bit, but on 2 bits it's not going to be able to correct still. That is still an evolution of what's going on. And then we talked about that, that summary that I was talking about. I should have moved that summary at the last of that, right? Maybe I was doing that when it was 2 o'clock or 3 o'clock at night and I was really half asleep. Okay, so single, dual, and triple channel memory. Standard memory controllers manage access to memory in chunks of the same size as the system bus's data width. So the thing is that standard memory controllers manage access to memory in chunks of the same size as a system bus's data width. In English, what it means, English just means that we need to understand, right? I just read a line and it's like, what? So the buses here, the bus speed, and those lines that we were talking about, right? So if their speed is suppose it is 168 kilobits per second or 2 megabits per second or 1 gigabits per second, the bus speeds also count. So the bus speed here, the speed of those small lines there should be the same as the speed of the memory here that is attained. So suppose the buses are giving you a lot of data, and memory is like not able to receive all that data and load all that data. So what's the so that's why when you purchase a motherboard, there's a specific type of memory that is compatible with the motherboard. You cannot have DDR on a motherboard that can support DDR3, they could have made that compatibility. But the way the DDR3 compatible motherboard will work, DDR RAM cannot take that. The bus speed of the DDR3 compatible motherboard will be much faster. They are sending a lot of data that way, and if it was DDR you were able to put, it would not take and load that kind of data. So DDR3 RAM should be there for the DDR3 compatible motherboard.
So it crash.
It would not load the data. It will give you so many errors. So it will not load the data. Not load the data mean you cannot see this. It's not loading. It's loaded right now in memory. We can. So it will not perform. It will give you errors after errors after errors.
And even it wouldn't go inside the slot because you said
Yeah. Suppose they made it compatible because they definitely did themselves. They, on purpose, they made it incompatible because the architecture will not support a slower memory. They are sending with bus speed that is much faster to a slow memory that doesn't make, it won't be compatible then. Do we understand what we're talking about? That's the main thing. You are putting some speed, the next one has to take that speed. It has to load that kind of data that is coming on that speed, right? So that's why the cuts are there. Hey, don't put slow memory on these kind of motherboards or whatever that kind is, right? So we understand that the bus speed and the memory really are in sync, must be. So obviously then the processor has to be in sync as well. Then every component has to be taking up that speed. If they are sending in that speed or receiving that speed, so everything should be upgraded level. Not only memory, processor should be also advanced, motherboard is advanced, so RAM should be advanced as well. A bus is a communication system that transfers data between components inside a computer or between computers. We talked about that before. So this expression covers all related hardware components, wire, optical fiber, and software, including communication protocol. So whatever data is coming from anywhere through a component to a component in the motherboard, it is because of, thanks to bus, right? And 2 o'clock there is a bus coming, TTC bus, right? TTC, okay. So this is considered, okay, my sound is like, my voice is changing, all of a sudden it's a different guy now, right? Now it's the same guy. Okay, so this is considered communicating over a single channel. What is considered? So when the bus is moving the data, it is sending it to the RAM, and RAM is loading that data. So this is considered communicating over a single channel. Most modern processors have a 64-bit system data bus, and if it is DDR2 right now, which I think it is, so it would be 64-bit, yes. But DDR3 would be also 64-bit. Now I was gonna say it would be 32-bit, but it's not 32-bit. 32-bit architecture is much slower, and it was 486, very old motherboards. You might be not seeing that anymore. 32-bit, right? It's all 64-bit right now. So this means that 64-bit just means that it's not the 32-bit processor will exactly look like the same as the 64-bit processor. It's the internal speed that will be different. So, but if you put a 32-bit processor on a 64-bit motherboard, it's not going to work, right? So the thing is that they all look the same. Internally, they won't be compatible, and the speeds will be different, right? So this means that a standard memory controller can transfer exactly 64 bits of information at a time. 64 bits of information in a bus is traveling at micro millisecond speed, and it's 30, instead of 32-bit chunk, it's 64-bit, bigger chunk of data is traveling in the bus. So single channel communication is a bottleneck, hence dual and triple channel came. So dual channel memory is the memory controller's coordination. Memory controllers coordination of two memory banks to work as a synchronized set during communication with the CPU, doubling the system bus speed width from the memory's perspective. In English, it means that two of the memory banks work together to load a application. Instead of one memory bank receiving a task and doing that, two combine together the effort to make the task faster, right? So that's why if each memory bank is full, not only that you increase the capacity, but they work together as well to get the task done, right? And task is memory just loads data. It's not like just loads data. That's the main thing that it's doing. That's the main thing.
It's
Yeah.
kind of like a dual core
Yes.
processor.
Core. That's a dual core in a processor, but that will be exactly dual slot or dual channel. We call it. Dual channel is two of the memory slots, two of the memory banks are working together.
Synchronized.
They are synchronized, right? So they are working together and they're making the task even faster.
So do they divide the tasks? Or?
Normally, yeah, they would become one, but with each of their capacity combined. So the task will be much faster. So dual channel memory is the memory controller's coordination of two memory banks to work as a synchronized set during communication with the CPU, doubling the specified system bus width from the memory's perspective. So from memory side, they said, hey, we are two working together now. Hey, bus, whatever you want to throw at us, yeah, go for it. Bring it on. We're ready for it. We are two or four memory banks working together now, so we can take all kind of data coming from CPU to us through the bus there, right? If it reaches on time, right? Not this bus, TTC. Oh, okay. So here, we still have a lot of time. Okay, let's go ahead. And so triple channel memory then demands the coordination of three memory modules. So dual channel, two memory modules, triple channel, three memory modules, right? So those are the three RAM slots that are working synchronized, working together. So it just gets speedier. Buffered and unbuffered memory. A buffer is a temporary storage area that takes some of the load off of the primary circuit. For instance, a network instance buffer can store inbound packets when the CPU is currently unable to give undivided attention to the packets. So buffer and register are interchangeable terms. So there is a area in the memory that can be queued up while the memory is still loading other data there, other applications there, processing other data. So buffer is that temporary storage area where it keeps that whatever is about to happen. So okay, there's another task here, I'm queuing up here. Are you still loading the previous application? Okay, so I'll just wait for that now. And this is called buffered memory, where you can just keep and queue the data there. So then once the other data is loaded, then this data, the turn for that data to be loaded will come. And so if we go for buffered and unbuffered area, would be obviously it's not queuing up the data, right? So I'm going to be cross questioning that in next class, which is tomorrow.
What's the buffer located?
On the memory, on any one of the chipsets here, on any one of the, it's part of the memory.
Is
Exactly.
there any limitation to store the buffer?
Oh, that we have to dig down. That what is the limitation? How much data can be buffered? Normally, it's a very small space, just like a page file.
Buffer level also overflows.
Yeah, buffer overflow happens definitely. Suppose it cannot take that kind of data. So suppose there's too much application coming there, and it already is stored. This only results when we are double clicking and opening applications after applications, expecting everything to work. So then it will finally, even the buffer will not work then when you are putting too much load there. So definitely, a buffer overflow is another term definitely. So but we understand buffer. Yeah,
This is all built inside the RAM, right?
this is in the chipsets.
There's
In
a
the
buffer.
chipsets. Yes. So buffer and unbuffered area. Buffered area would be that will queue up the task that is about to happen. It's just waiting for the rest of the task to finish first. And it may not finish, like like it's just loaded and you're watching YouTube, you're watching Word, Excel, PowerPoint, you're watching everything, and you're not closing it. So the buffer will also then, and you double click something and you're waiting for it to happen, and you forgot it and you're still looking for other things. It is in the buffer and it's waiting for other things to, hey, can you give me some space here so I could load as well. So other than page file is also done. So
So this is kind of what's the difference between a buffer and a page file?
actually this is buffering when memory still have some space there. This is after that, when it's run out of total space there,
Then it goes to
then it goes to
last
page.
resort.
Page file is the last resort always.
So where is the page file located? Is it in the memory as well?
No, page file is part of the hard disk that is used as a memory. It is a hard disk, but it is used as a memory temporarily. So page file normally is 2 GB, 3 GB, 4 GB, 5 GB.
So the same
Yep.
idea of the cache memory as well.
Yes, it's same idea of cache memory as well. It's
What's the difference
yeah.
between
So it's queuing there. It's just loading the data. Cache is about very fast access again. So the speed, cache is always about speed. Cache equals speed. This buffer is just you're waiting, 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 waiting. So it has nothing to do with speed. Yeah, cool. So and we talked about that. So now this slide I have to really reorganize it because now this topic is coming synchronous, asynchronous, SDR single data rate. That this slide should have been on the start, but we're seeing at the end of it. And I don't know why I'm looking at the clock. While I have a clock here as well. Oh, actually I don't have a clock here. The slide is covering the whole thing. So it's okay, it's legit to see that clock, right? Memory comes in many formats to meet particular application needs or affordability for consumers. So DRAM, when you expand the memory in a computer, you are adding DRAM chips. Dynamic refers to the memory chip's need for a constant update signal, also called a refresh signal. Oops. In order to keep the information that is written there, if this signal is not received every so often, the information will bleed off and cease to exist. So the thing is that this is dynamic memory, and the data is there as long as the computer is powered on, and that's pretty much what it's saying for this really old RAM, DRAM there, dynamic memory, right? There was static memory there as well. So most popular synchronous DRAM, SDR, DDR2, DDR3, and synchronous DRAM shares a common clock signal with the computer system bus clock. So if your bus speed is whatever the bus speed is, that it keeps that speed here in the RAM as well. So which provides the common signal that all local bus components use for each step. So this characteristic ties SDRAM to the speed of the FSB. Seriously, now they have to include FSB as well. Now we talked about FSB at the start, I guess. Oh, so what is FSB? So FSB is a front side bus, and it is a bus that is communicating the chipset that is nearest to that, the North Bridge chipsets. It is the bus is connected to the North Bridge chipsets and to the processor. So FSB is that which connects the nearest chipsets to the processor, right?
Can you explain it one more time? I don't know.
FSB we discussed when you were not here, so we discussed in the first hour. No, I just want to make you feel a little miserable, and then I'm gonna explain anyway. Yeah. So you should be like, oh man, why?
I
Yeah.
came like 26.
So 25 minutes we discuss so much, and normally the critical things I discuss in first 25 minutes, and tomorrow it will be even more critical stuff.
I can.
So as soon as you come, then I will go for less critical stuff. Yeah. Okay. Now this is just RAM and then. Okay. Just kidding. Okay. So yeah, but please try to come early because if you miss the first minute of the class, we could have discussed something. On the basis of that, we will discuss the second thing. On the basis of that, we will discuss the third thing. If the first thing is not clear, nothing. Then it's incomplete map, right? So try to come on time, right? The class is at 9 o'clock. 9 o'clock. If it is 10 o'clock, you're coming at 9:30, 10:30. So 9 o'clock, 9:30. Yes. Oh. Okay. So. So yeah. So for everyone, class is 9 o'clock psychologically. Right? So that's psychological time. Okay. So here. Let's just go for what we were talking about is just that the bus speed. If it's SDRAM, synchronous DRAM, it just synchronizes itself with the clock signal, which is just the speed of the bus, right? But yeah, you were talking about then FSB. Now FSB. Oh yeah, there you go. Thank you. Welcome to the class. Okay, so yeah, FSB is front side bus. So front side bus is, I'm just separately saying that. So let me just create a diagram for that quickly because that's a very good question by OS. It is something that we should know. So suppose this is a processor socket here, right? And this is a socket right? Processor socket. So it's processor socket. It's not zers. Okay, and then there's a chipset beside it, and the chipset beside it, and the chipset beside it. Now the North Bridge chipset, V the North. It's not V the North. Yeah. So those chipsets are they need to communicate with the processor, right? Not with chipsets. So these chipsets are communicating with the processor with the help of buses. So these buses, which are helping the nearest chipsets, the North Bridge chipsets, communicate with the processors. So these are called FSB. So this guy here is FSB. This
So they're
bus
connected.
here is,
The North Bridge to the processor.
yes, exactly. You're right. FSB, FSB. Front side bus. Front side bus. Right? So that's a good question.
And then BSB connects South Bridge.
Yes.
Processor.
You did this course before. Now I know.
I see it from the notes.
Okay. Okay. So exactly. So the other types of buses would be for the slower South Bridge processing,
The
right?
less important.
Yeah, less
chipsets.
important.
The
Hey, you
less
know
important.
everything, man. Okay.
Mm,
Okay, that's good. That's very good.
Well,
Mhm.
that last slide, I still don't understand some of the points on it.
Yes, sir.
The that second point.
Yeah. So synchronous DRAM shares a common clock signal with the computer's system bus clock. So which provides the common signal that all local bus components use for each step that they perform. So the clock signal normally is the speed at which you are going and performing the tasks, right? So the processor has a clock signal, the RAM has a clock signal, the bus, they have to be resonating at the same speed there. So if there's a lot of data coming here, that lot of data has to be at once received properly and has to be loaded properly at the same. So it's just saying that synchronous DRAM just that a RAM that synchronizes itself with the speed of the bus and with the speed of the processor as well later, right? So if the bus is sending data fast, the RAM has to receive it fast and load it fast
So it's
or
called
execute it fast.
So it's called synchronous DRAM.
Yes,
It adapts to what the buses are saying.
that's it. You put it that perfect wording. Yeah. So yeah, that's very good. So yeah, that's great. I was gonna say that if you were, on time, see how much you can achieve then, right? So yeah, and so here the characteristic, yeah, we already talked about that. No, not this. This characteristic ties SDRAM to the speed of the front side bus, and hence the processor, eliminating the need to configure the CPU to wait for the memory to catch up. They are all caught up. The speed of the processor, the speed of the bus, the speed of the RAM, they're all synced or synchronized together. Processor sends something, buses send it on the same speed, the RAM receives it on the same speed, and execute it on the same speed. If the speeds are different, it's gonna be errors. It's gonna be, the work will not done. The things will not load on the memory properly,
So
and
are
errors
all,
will come.
Are all RAMs not synchronized or?
They're all synchronized. They have to be, otherwise it's not gonna work. The basic operation will not work. Operating system will not start. If operating system is loading a lot of files there, the processor is processing those files, and then the bus is saying and taking that data to the RAM. So it has to work the same way. They're all supposed to be synchronized. Okay, so that's what we understand there, and yeah, it's a unique slide that keeps on talking about. Well, then there is SDRAM, DDRAM, DDR2, DDR3. SDRAM is now considered a legacy RAM, so it's like pretty much gone, and it is presented here only to provide a basis for the upcoming discussion of DDR. And with the SDR, SDRAM, every time the system clock ticks, one bit of data can be transmitted per data pin, limiting the bit rate per pin of SDRAM to the corresponding numerical value of the clock's frequency. Seriously, are you kidding me? See, that was so simple and straightforward. Whatever they said. At the end, when you say whatever they said, it was so simple and straightforward. And then you say whatever they said. So this means we didn't get it. But normally it is that limiting the bit rate per pin. How many pins are there? How many? Huh? Yeah, you were saying that. 252? No. There was a set of pin 168 pins, and there was another 240. So this is 240 pin and standard. Now it's you will see 240 pins, right? So pin bit rate per pin. Each pin, there are 240 pins here, and if you start counting very near, yeah, they look like, actually they don't look like that. So anyway, so each pin receives one bit, second pin receives one bit, one bit, one bit, one bit, one bit, 100. 240 bits can be received per pin inside the RAM and then executed in the chipsets, right? So it's limiting the bit rate per pin. Then it can receive all. Suppose there's 240 pins, but it is not bit per pin. Maybe it sends you 500 bits instead of 240 bits. So 500 bits have to wait a little, right, to be entering from or being received by the pin, right? 240 pins. So it's like the main gate should be as wide as the traffic is coming.
So the buses can carry them to 40 bits to the RAM.
Yeah, so that's it. Just yeah. So if it is 240 pin compatible motherboard, it's gonna send that much data that can be received easily by the with the fast rate at that same rate where the way it is sent. It's gonna send that much that it can receive, so it will receive properly, right? So, and DDR SDRAM double data rate SDRAM earns its name by doubling the transferring rate of ordinary SDRAM. So because you have now chipsets on the two sides, it can receiving capacity and then executing capacity is double now. Well, that is like decade ago. We're just talking about that. DDR2, think of the 2 in DDR2 as yet another multiplier of 2 in the SDRAM technology, using a lower peak voltage to keep power consumption down 1.8 volts versus the 2.5 volts of DDR. So when you use up more voltage, it heats up more. If you're doing the same work with lesser voltage, that's better. You don't heat up, the memory sticks don't heat up fast, right? So that's just a technology that they have added. Plus the data DDR3, the next generation of memory devices, they're saying next generation. This is like 6 or 7 years ago. So like A plus is like that. Even 1001, you have the latest book. So guys, we can have that book from library. That A plus book, you got it from library, right? This one. So and but it is on hold, as you said. That people do put it on hold.
You get an ebook too.
Ebook version of that in the library.
Yeah.
Okay, ebook can be. They don't put it on hold, or I think the ebook is also put on.
Yeah, they put on hold sometimes too.
Ebook says
Yeah.
because we don't download that, right? So it has to be one connection, and I don't know. No, we never. So we don't download. That's why they put it on hold. Then I guess ebook can be on hold.
Yeah.
You're saying?
So
Actually, I remember that one book I really needed that an
If it's
ebook
a-
version.
If it's a unicast.
1-to-1, one session only. That's it. That was on Network Plus. Good man. Only that somebody needs to reach on time. So it's psychologically 9 o'clock, right? So yeah. So okay, guys. Here, DDR3 SDRAM, the next generation of memory devices, was designed to roughly double the performance of DDR2. So products, DDR2 products 2 and 3 are not multipliers but versions, revisions of that. So it's not like you double the speed when it is 2. It's just we revised it, we named it a new version, we added some more features, right? Hence DDR3. So it's 7 minutes more. After that, we're going to be starting a big lab till 3:30. So yeah, in hardware we're limited. In network we're gonna have a lot of lab. I do every course with lab. So A plus is like, they gave me, normally I teach advanced applications, cloud, VMware, MCSA, all those. VMware, well, especially VMware, it's really extensive. So, but this is hardware itself is limited, so I'm also limited to, okay, what do I do now? Because that's it. Take out the components, put it back. The rest is all theory. But there is virtualization here now. And in next class, maybe we will go to that other room and we will have to create the virtual machine for that. But we're gonna go for the virtual hardware aspect of those virtual machines. But it's without labs, the course is like not good. But I was saying that at till 3:30 we're gonna do that, or till 4 o'clock, right? The other students know that already. That I'm looking for a reaction. No, please.
No, this is why I registered for this course. Basically for the lab more than the theory.
Yeah. Well, the thing is that I could take out 50 or 20 labs if there was any possibility. Now, if they're talking about chipsets, if you saw that animated movie like Magic School Bus, Magic School Bus, they would just really become tiny. They would go inside and actually do the practical of, whoa, what is this? Oh, that's how it works. So I wish we could be Magical School Bus, and we could be really shrunk to tiny and go inside the chipset. But we can't do that. I mean, in hardware, I'm scratching my head. Where is the lab? I mean, in RAM, you did the lab, took the RAM out, put the RAM back.
Why? There are so many things we can learn.
Yes.
I mean,
Yes. So yeah, any suggestions are welcome. But otherwise, in RAM, I don't see anything other practical other than taking out the RAM just for RAM. Give me any other lab there. I would just do that. I would just implement. I'll make a bigger version of that, right? But other courses, suppose MCSA, if you do, you would not have a single second to scratch your head. It's like it's all click. We configure applications the way I've configured in banks. I was working in Scotia Bank before 5 years, system administration, and without practical labs, I don't teach a course. Here, I just need to pay bills, so I'm here. Otherwise,
we
but
all the same.
yeah, but if there was any lab, I would do it. Just suggest me one. This is the most limited course, Network Plus. There are so many labs. That's on Thursday and Wednesday and Thursday. So, but we are already in the middle of a lab actually there, right? Those who are continuing that course as well. But here, yeah, if there was a lab, I would have definitely gone. I call myself lab freak. I have to have a lab to teach a course, right? That's good. You have a passion to do the labs. That's very good. For other courses, it will really be satisfied that passion. Here, I'm coming up with what can I do? I take out the buses there and see those the buses. Let's connect them together. Okay. So, but I cannot think of any. So FSB in megahertz times 8 bytes. Now I don't know why I'm looking for time. Normally students are seeing like this time like this and then showing me teach time. Really? So but we're gonna still go for till 4 o'clock, right? You're saying thank you. These guys know what I'm doing right now. I'm just kidding with them. At 2 o'clock, we're going anyway. Right?
Oh,
No, she's generally looking for a class. She generally wants to learn.
I was
She's
like,
not.
That doesn't mean, but you might have something somewhere else to go.
Oh, I have. It's
That's
on my
the
tab.
point.
So,
That's what I'm thinking.
so what are you saying? There's a lab.
no. I was just joking at that time, so I would see your priceless reaction.
Okay.
That no, I'm gonna go at 2. Come on, don't. So normally that priceless reaction is there, right?
If you said another half hour, then I'd be like, oh, man, you said like
4 o'clock.
There's no way.
Yeah, it's just that
Are you gonna go George Rock teach?
Tuesday and Thursdays. Yeah.
Are you teaching the same course?
No, there it's this is the only course where I unwillingly am teaching this one A+. All other courses so there is SQL Server and that's Exchange Server, email server and database server.
So it's downtown. Right?
Downtown Casaloma campus. And here also other courses on Saturdays. It's like cloud courses, all labs, VMware courses, all lab, big networks. We're creating 5 virtual machines. We're connecting IP addresses, going pinging everything. It's total 4 hours of lab.
Does George Rock, did they go at the same speed as this, or is it more toned down? Is it toned down?
We have to follow the public college rules there. So
So it's less.
no, it's much more speedier than this. So
Much more speed.
depends on the professor. I just go for all the labs, and it's like they don't have time to scratch their head as you know. But we go for theory, then lab, then theory, then lab. It's the same style, but I have to tone it according to the public colleges there, which is not much. I don't change. They make me change, then I just go back to what I do. So they like that too, but they want to still change it. It's just that if we don't do labs, it's like driving and swimming. You can't drive or swim if you don't do it yourself, right? So this is one limited course where I am like hands behind my back, like what do I do next? How? What else is there for RAM? Or what else is there for processor? I asked them to take out the processor and put it back. That's it. Okay, let's go ahead. Seriously, what else we can do? You tell me, I'll do that. Right there, YouTube is full of ideas, right? So, hey guys, so we're gonna carry on tomorrow at 9:55. Okay, and 9:55 we're gonna carry on, and but we're gonna talk about hard disks. I'm gonna be taking out the hard disk there, and we will be still assembling and disassembling the whole computer. That's where you need to be very careful, and there will be screwing and unscrewing. So please bring your screwdrivers there. No, just maybe we have 2 or 3. But you as A plus guys have to have your own screwdrivers as well, the multiply and minus both, right? I'm just saying that, but yeah, we'll provide that. Alright guys, so see you on 9:55 tomorrow. We're gonna continue with that, and hard disk, motherboard we have talked about, processor we need to talk about, then some other components we're going to go for. Now there are virtualization and virtual components, and I think they have cloud here, or actually the cloud is actually in CompAPlus, but we have to go for virtual environment where there's a lot of labs there. So yes, we're going to continue with this hardware, but hardware is just one section of A plus now. It's not the whole thing anymore. So yeah, so we'll that's it. I'm just going to stop the class, and thank you.